Newtonian mechanics is where the modern story of physics begins. It's a branch of classical mechanics that describes the motion of objects under the influence of forces formulated in the 17th century by Sir Isaac Newton. Imagine it as the physics of everyday life, the reason you can throw a ball and predict, almost instinctively, where it's going to land. It's how we can calculate the path of planets, predict the time of sunrise tomorrow, and launch rockets into space. At its heart, Newtonian mechanics boils down to a few simple laws that change the way we understand the universe. Let's start with Newton's first law, sometimes called the law of inertia. An object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. This means that if you were to kick a ball across a perfectly smooth, endless surface, it would keep moving forever. Of course, that doesn't happen in real life because of forces like friction, which gradually slows it down. But in a vacuum, with no resistance, the ball would keep rolling eternally. This simple observation that objects maintain their state unless interfered with was revolutionary. Before Newton, many believed objects naturally slowed down and stopped due to their own qualities. But Newton showed us it was forces, or lack thereof, that dictated motion. Newton's second law connects force, mass, and acceleration, Fma. This is probably the most famous formula in all of physics, and it's incredibly intuitive once you break it down. If you have a heavy boulder and a small pebble, the same push won't make them move in the same way. The boulder, with its greater mass, would require far more force to achieve the same acceleration as the pebble. This law is not just theoretical. It's the reason why engineers can calculate how much fuel a rocket needs to reach a certain speed, or why designers can determine how fast a car can accelerate based on its weight and engine power. Finally, Newton's third law states, for every action, there is an equal and opposite reaction. When you push against a wall, it pushes back with equal force. This law is evident in all interactions. Think of a rocket engine. As the engine expels exhaust gases in one direction, the rocket itself moves in the opposite direction. Or picture a swimmer pushing water backward to propel themselves forward. Newton's third law encapsulates the way the universe balances forces. One of Newton's crowning achievements was the universal law of gravitation. It states that every mass attracts every other mass with a force that's proportional to the product of their masses and inversely proportional to the square of the distance between them. Simply put, if you double the mass of an object, the gravitational pull it exerts also doubles. If you double the distance between two objects, the gravitational force weakens to a quarter of its original strength. This law applied not just to apples falling from trees, but also to planets orbiting stars and moons orbiting planets. Newton's law of gravity allowed people to understand why planets orbit the sun in predictable paths. It explained the behavior of tides, the orbits of moons, and even the path of a cannonball shot from a hilltop. The same force pulling an apple to the ground is also what keeps the moon in orbit around the Earth. This concept that a single predictable force governed the motions of everything from small objects on Earth to celestial bodies in the heavens was nothing short of radical. Newton essentially unified the heavens and Earth under one rule, a revolutionary concept at the time. The impact of Newtonian mechanics extends beyond science to engineering, space exploration, and even day-to-day activities. For example, knowing that force equals mass times acceleration lets engineers design airplanes and predict how they'll respond to various atmospheric conditions. Newton's laws also govern the way we construct buildings, ensuring they can withstand forces like wind and earthquakes. Calculations derived from Newtonian mechanics are the reason why structures can be built taller and stronger than ever before. Space exploration would be impossible without these principles. When scientists calculate the trajectory of a spacecraft, they're using Newtonian mechanics to chart the course. They must consider the gravitational pull of various planets and celestial bodies and use the laws of motion to understand how different forces will alter the path of the spacecraft. Even though today's physics incorporates more advanced theories, Newtonian mechanics remains the basis for understanding most of these movements on a practical level. Newtonian mechanics works remarkably well for most everyday purposes. However, as scientists started examining things on extremely small or large scales, they noticed its limitations. When objects move at speeds close to the speed of light, or when they exist within intense gravitational fields, Newton's laws don't fully apply. This is where Einstein's theory of relativity comes into play. Likewise, at the atomic and subatomic scales, quantum mechanics takes over, as Newton's laws can't account for the strange, probabilistic behaviors of particles. Despite these limitations, Newtonian mechanics remains one of the most robust frameworks in science. It may not explain everything, but it explains a lot, with impressive precision, in the world we interact with daily. Newton's laws of motion and gravitation continue to serve as the bedrock of engineering, mechanics, and classical physics. In many ways, Newtonian mechanics reflects the power of simplicity. A few basic laws govern an astonishingly wide range of phenomena. Newton's work shows that complex motions and interactions can be understood through simple principles, a lesson that laid the groundwork for the more intricate theories that followed. Thermodynamics. Thermodynamics, at its core, is the study of energy, heat, and work, and how these elements interact in physical systems. Imagine thermodynamics as the science of change. It's all about understanding how energy moves and transforms in everything from engines and refrigerators to stars and black holes. It provides rules for what's possible and impossible in our universe, from why a cup of coffee cools down over time to why we can't build a perpetual motion machine. To truly grasp thermodynamics, let's explore its 4 fundamental laws, each of which adds a new layer to our understanding of how energy operates in the world around us. The 0th law of thermodynamics, though often overlooked, lays the groundwork by defining what temperature is and how it can be measured. Imagine 3 objects. If object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then A and C must also be in thermal equilibrium. This transitive property is what allows us to say that 2 objects at the same temperature, even without touching, will not exchange heat. Think of the 0th law as the rule that makes thermometers meaningful. If you place a thermometer in a glass of water, you can trust the reading because the thermometer reaches thermal equilibrium with the water. This law may seem simple, but it underpins our ability to measure temperature consistently and reliably. The first law of thermodynamics is essentially the law of energy conservation, stating that energy cannot be created or destroyed, only transformed. It tells us that the total energy in a closed system is constant. Imagine you're pushing a boulder up a hill. Your work, input energy, is stored in the boulder as potential energy. If you let it roll down, that potential energy transforms into kinetic energy as it gains speed. In other words, energy flows and changes forms, but the total amount remains constant. This law is the reason why you can't get more energy out of a system than you put into it. It's a fundamental limit on what's possible in engineering and physics. For instance, in an internal combustion engine, the chemical energy in gasoline is transformed into heat, which then transforms into mechanical work to power your car. But some energy is always lost as waste heat. It's not destroyed but spread out in a less useful form. The first law essentially tells us that all processes involve energy transformations, but we can never get something from nothing. If the first law is about the conservation of energy, the second law of thermodynamics introduces us to the concept of entropy. Entropy is a measure of disorder or randomness, and the second law states that the total entropy of an isolated system can only increase over time. This principle gives us what's known as the arrow of time, a clear direction in which time flows. Imagine a deck of playing cards. If you shuffle it thoroughly, the order becomes more random, an increase in entropy. Reversing that process, Returning the deck to a perfectly ordered state through random shuffling is practically impossible. Similarly, if you spill cream into your coffee, the two will mix together, increasing the disorder, and it's nearly impossible to separate them again. The second law also explains why heat naturally flows from hot objects to cold ones. When you put a hot mug of tea in a cooler room, the heat flows outward, increasing the overall entropy as the tea cools and the room slightly warms. This law is what makes perpetual motion machines impossible. They would violate the natural increase of entropy in a closed system. In other words, every energy transformation has an inherent cost. Some energy will always be lost to entropy. The third law of thermodynamics is perhaps the most abstract but equally profound. It states that as the temperature of a system approaches absolute zero, 0 Kelvin, or minus 273.15 degrees Celsius, the entropy of the system approaches a minimum value, usually considered zero. Absolute zero is the lowest possible temperature, where all atomic motion theoretically stops. While it's impossible to reach absolute zero exactly, this law helps scientists understand the behavior of systems at extremely low temperatures. At temperatures near absolute zero, materials start to behave in strange and unique ways. For instance, certain materials become superconductors, allowing electricity to flow with zero resistance. The third law also implies that you can never quite reach absolute zero because removing that last bit of heat becomes exponentially harder as you approach it. Thermodynamics is woven into the fabric of everyday technology and natural processes. Refrigerators and air conditioners, for instance, operate on cycles that leverage the principles of thermodynamics. They extract heat from a cooler area and release it into a warmer one, which seems counterintuitive until you understand that they're driven by an input of work, usually in the form of electricity. Another example is the steam engine, one of the earliest and most impactful applications of thermodynamics. In a steam engine, water is heated to produce steam, and this high-pressure steam drives a piston, turning heat energy into mechanical work. Understanding the limits of efficiency in these engines paved the way for more advanced and efficient machines, from cars to power plants. Thermodynamics is also critical in understanding astrophysics and the life cycle of stars. Stars burn their fuel through nuclear fusion, a process that releases an enormous amount of energy but also generates entropy. Eventually, as stars exhaust their fuel, they undergo transformations, expanding into red giants or collapsing into white dwarfs, neutron stars, or black holes. This progression follows the principles of thermodynamics, where energy transformations and entropy drive the life cycle of these celestial bodies. Thermodynamics doesn't just describe mechanical systems, it applies to any system where energy changes occur, from biological organisms to cosmic events. At its essence, thermodynamics gives us a structured view of why energy changes are often irreversible and how energy disperses in systems, providing both elegance and limits to what we can achieve. By showing us the boundaries of efficiency and the inevitability of entropy, thermodynamics also serves as a reminder of the universe's irreversible nature. In a sense, these laws mirror life itself, structured, dynamic, and governed by change. And while we can't violate these laws, we can manipulate them within their constraints, creating technology that harnesses the power of energy while acknowledging the inevitable costs. Thermodynamics is a beautiful balancing act between energy, heat, and work, revealing the invisible rules that govern everything from the simplest cup of coffee to the engines of the cosmos. Electromagnetism. Electromagnetism is a fundamental force of nature, responsible for everything from the light that illuminates our world to the power that drives our technology. It's the dance between electric and magnetic fields, woven into the fabric of our universe and governing how charged particles interact. Imagine it as the invisible yet omnipresent force shaping much of what we experience daily, from magnets clinging to refrigerators to the devices we carry in our pockets. To understand electromagnetism, Let's break it down into its key components: electric fields, magnetic fields, and the principles that link them together. This story of electric and magnetic forces began with ancient observations and culminated in a unified theory that changed the course of physics. The story of electromagnetism begins with electricity. Ancient Greeks noticed that when they rubbed amber against fur, the amber could attract small objects like feathers. This strange phenomenon was an early encounter with static electricity, an electric charge built up by friction. Today we know that electric fields originate from electric charges, which come in two types: positive and negative. When charges accumulate on an object, they create an electric field, a region of influence that can exert a force on other charges. Picture electric charges as tiny actors on a stage, each with a role. Positive and negative charges are like opposing characters. They attract each other, whereas like charges repel. This attraction and repulsion are governed by the electric field, which radiates outward from any charged object. The strength of this field determines the force exerted on other charges within it. This is why a balloon rubbed on your hair can stick to a wall. Its surface has accumulated a charge that interacts with the charges in the wall's surface, creating an attractive force. While electric fields come from charges, magnetic fields arise from moving charges, specifically those that flow as electric current. Ancient civilizations discovered magnetism through lodestones, naturally occurring magnetic rocks that could attract iron. But it wasn't until the 19th century that scientists like André-Marie Ampère and Michael Faraday unraveled the connection between electricity and magnetism. Imagine magnetic fields as lines that loop around current-carrying wires, somewhat like ripples created by a stone thrown into water. These magnetic lines form closed loops, always finding a way to return to their source. Magnets, like the ones you see on refrigerator doors, are permanent sources of magnetic fields. Inside these magnets, tiny atomic particles called electrons are moving in a way that aligns them and creates a stable magnetic field. So, the most fascinating thing about magnetism is that it isn't isolated. It's inherently linked to electricity. Wherever there's electric current, there's a magnetic field, and this connection is a cornerstone of electromagnetism. The unity between electric and magnetic fields was first proposed by Michael Faraday. He discovered that a changing magnetic field could induce an electric current in a nearby wire, a phenomenon now known as electromagnetic induction. Imagine a magnet moving through a coil of wire. The changing magnetic field generates a current in the wire. This discovery forms the basis of electric generators, which convert mechanical energy into electrical energy by moving a magnet near coils of wire. Electromagnetic induction is the reason we have electricity today. The rotating turbines in power plants work on this principle, transforming the kinetic energy from wind, steam, or water into electrical energy, which flows through the power lines to our homes and cities. Faraday's work showed that electric and magnetic fields are two sides of the same coin. Where there's one, there's the potential for the other. The true breakthrough came when James Clerk Maxwell formulated his famous equations, 4 mathematical statements that united electric and magnetic fields into a single framework. Maxwell's equations describe how electric charges and currents create electric and magnetic fields, and they reveal that changes in these fields can propagate as waves. Imagine a moving charge creating a ripple in the electromagnetic field, much like a pebble dropped in a pond. This ripple travels outward at the speed of light. Maxwell's equations showed that light itself is an electromagnetic wave, a fluctuation of electric and magnetic fields traveling through space. This discovery was revolutionary, as it linked visible light to a vast spectrum of electromagnetic radiation, including radio waves, microwaves, X-rays, and gamma rays. The implications were profound. Light, radio signals, and all forms of electromagnetic waves were simply different frequencies of the same underlying phenomenon. The entire electromagnetic spectrum became a new frontier, enabling technologies like radio, television, radar, and even Wi-Fi, which all operate using specific frequencies in this spectrum. Electromagnetism is responsible for nearly every modern technology. Electric motors rely on the interaction between electric currents and magnetic fields. In a motor, electric current flows through coils, generating a magnetic field that interacts with permanent magnets, creating rotation. This principle powers everything from household appliances to electric cars. Transformers, another application of Faraday's induction principle, allow us to efficiently transmit electricity over long distances. By stepping up the voltage for long-distance transmission and stepping it down for safe household use, transformers make our power grids viable. On a smaller scale, electromagnetism governs the behavior of atoms and molecules, shaping the structure of matter. The way electrons orbit an atomic nucleus and interact with other atoms relies on electromagnetic forces, as do the bonds that form between atoms in molecules. This is why chemistry exists at all, because electromagnetism holds matter together and dictates how atoms can combine. With the advent of quantum mechanics, our understanding of electromagnetism gained new depth. In quantum theory, electromagnetic interactions are mediated by particles called photons, which are essentially quanta of light. When two charged particles interact, they exchange photons, which carry the electromagnetic force between them. This quantum perspective explains why electromagnetic forces are incredibly strong and able to act over vast distances compared to gravity. Electromagnetic forces are responsible for nearly all phenomena we experience directly. Chemical reactions, material properties, and even the way our eyes perceive light all stem from electromagnetic interactions. In a way, this force shapes our everyday reality more than any other. Electromagnetism, with its intertwining electric and magnetic forces, is one of the most studied and utilized forces in physics. It bridges the macroscopic world we experience and the microscopic world of particles and photons, bringing coherence to everything from simple magnets to the most advanced telecommunications. Its principles have transformed our world, enabling us to harness energy, communicate over vast distances, and explore the atomic and cosmic scales. Through electromagnetism, we've learned that even the invisible forces around us have an elegance and consistency that reveal the underlying beauty of our universe. And as we continue to explore the limits of electromagnetism, from quantum computing to medical imaging, we see just how profoundly it shapes and enables the unfolding story of human progress. Special relativity. Special relativity, formulated by Albert Einstein in 1905, revolutionized our understanding of space, time, and motion. Before Einstein, scientists believed that space and time were fixed, absolute frameworks within which objects moved. But Einstein showed that these seemingly concrete notions are, in fact, interconnected and flexible, transforming how we view reality itself. Imagine you're standing on a train platform, watching a train zoom past at an incredible speed. For you, time feels the same as ever. You can feel each second ticking by. But for someone on board the train, moving at high speed, time might actually feel different. This concept, that time can stretch or shrink depending on the speed at which one is traveling, is one of the core ideas of special relativity, often referred to as time dilation. To understand how special relativity works, it helps to start with Einstein's bold assumption: the speed of light is constant. Regardless of whether you're moving toward or away from a light source, light always travels at a fixed speed of about 300,000 kilometers per second. This might seem strange at first because we're used to thinking that speeds should add up. If a car speeds toward you while you're walking toward it, the car's speed would seem faster from your perspective. But light doesn't follow this logic. It remains constant, regardless of any observer's motion toward it. This constancy of light speed forces us to rethink the structure of space and time. Imagine that the speed of light is like a universal speed limit. No matter how fast you go, you can never exceed or even match this speed, But what happens as you get closer to it? One of the most mind-bending predictions of special relativity is time dilation. Picture two twins. One stays on Earth while the other travels in a spaceship close to the speed of light. According to special relativity, the twin on the spaceship would experience time more slowly than the twin on Earth. If the astronaut twin returns to Earth, they would find their sibling has aged significantly more. This phenomenon, often called the twin paradox, isn't just theoretical. Scientists have confirmed time dilation experimentally using precise atomic clocks in high-speed jets and satellites, where clocks in motion run slightly slower than those on Earth. The reason for time dilation lies in the relationship between time, space, and the speed of light. If light speed is constant, then space and time must adjust themselves for different observers. At high speeds, time slows down to ensure that everyone still measures light moving at the same pace. So, while time feels normal to each individual, the rates at which time flows are not absolute. They depend on the observer's velocity. But special relativity doesn't just affect time. Space itself is also flexible, a phenomenon known as length contraction. According to this principle, objects traveling near the speed of light appear shorter along the direction of their motion. Imagine you're observing a spaceship hurtling by at close to light speed. To you, the spaceship would appear squished in the direction it's moving, almost like an accordion. The faster it goes, the more it appears to contract. This contraction isn't a trick of perception. It's a real physical effect due to the interwoven nature of space and time. In the astronaut's frame of reference, everything seems normal. They don't feel any shorter or squished. But from the viewpoint of an outside observer, space has adjusted to accommodate the constant speed of light. Another counterintuitive concept in special relativity is that simultaneity, the idea that two events happen at the same time, is not universal. Suppose two lightning bolts strike either end of a moving train. An observer standing on the platform may see both bolts strike simultaneously, but an observer on the train might see one bolt strike before the other. This isn't because of any delay in perception, but because the concept of simultaneous is relative. It depends on the observer's motion. This relativity of simultaneity illustrates that there is no single universal now that applies to everyone. For us on Earth, now might mean October 26, 2024 at 3 p.m. But for someone on a spaceship hurtling through the cosmos, moving close to the speed of light, what constitutes now might differ from ours. In the vast tapestry of space and time, what one observer considers as present can be the past or future for another. One of the most famous outcomes of special relativity is the equation E=mc squared, which links mass and energy. In this equation, E represents energy, m represents mass, and c is the speed of light. It suggests that mass and energy are interchangeable. They are two forms of the same thing. This concept is not just theoretical. It's the reason nuclear reactions produce such tremendous energy. In atomic bombs and nuclear reactors, a small amount of mass is converted into a massive amount of energy. The equation tells us that even a tiny amount of mass, multiplied by the square of the speed of light, can release vast amounts of energy. Special relativity thus reveals a deep connection between matter and energy, showing that mass itself is a form of potential energy. Special relativity might seem esoteric, but its effects are woven into our daily lives. For example, the Global Positioning System, GPS, relies on a constellation of satellites orbiting Earth, each equipped with highly accurate atomic clocks. These satellites move at high speeds relative to the surface of Earth, which means that, according to special relativity, time ticks more slowly for them. Engineers must correct for these relativistic time differences, otherwise GPS readings would be wildly inaccurate, placing you miles from your intended destination. The principles of special relativity also influence other technologies, such as particle accelerators. When particles are accelerated to near light speeds in machines like the Large Hadron Collider, their mass effectively increases, requiring more energy to accelerate them further. This effect is a direct consequence of special relativity, shaping the design and function of cutting-edge scientific equipment. Special relativity challenges our intuitive sense of time and space, suggesting that they are not rigid backdrops but flexible and responsive. It reveals a universe where time and space are woven together, where the notion of simultaneity dissolves, and where even mass and energy are deeply intertwined. In a way, Einstein's theory invites us to expand our understanding of reality, to think beyond the familiar, and accept that the universe operates in ways that often defy common sense. This is one of the most remarkable aspects of special relativity. It pushes the boundaries of human perception and invites us to explore the vast, interconnected fabric of the cosmos with fresh eyes and a sense of wonder. General relativity. Imagine you're standing in an elevator, and suddenly the cables snap. The elevator starts to plummet, and for a brief moment you feel weightless, as if gravity has disappeared. This simple experience is at the heart of Einstein's general theory of relativity. Einstein, looking for answers about the universe's structure, realized that gravity might not be a force pulling objects together, as Isaac Newton once thought, but rather the result of how objects move within the very fabric of space and time. In our everyday life, we tend to think of space as a flat and unchanging grid, like graph paper. But Einstein envisioned space differently. He saw it as a flexible, bendable fabric. Space and time are interwoven, forming a space-time that can curve, stretch, and warp in response to mass and energy. When a massive object, like a planet or a star, sits in space-time, it creates a dent, causing smaller objects nearby to fall into it. To picture this, imagine placing a bowling ball in the middle of a trampoline. The weight of the ball stretches the trampoline, forming a depression. If you roll a marble near the edge, it will spiral toward the bowling ball, not because the bowling ball is pulling it in, but because the shape of the trampoline guides the marble's path. Similarly, Earth warps the fabric of space-time, and the Moon orbits Earth not because of a literal force pulling it inward, but because it is following the curved track created by Earth's mass. Einstein's general relativity redefined gravity as the curvature of space-time itself. This approach was revolutionary, flipping the traditional view of gravity on its head. Under general relativity, massive objects tell space how to curve, and curved space tells objects how to move. This framework is beautifully summarized in the phrase, "Matter tells space how to curve, and space tells matters how to move." Einstein's insight was groundbreaking, but he didn't stop there. He developed mathematical equations to describe this curvature, known as the Einstein field equations. These equations are complex but elegant, capturing how mass and energy dictate the structure of space-time. In regions with intense gravity, such as near black holes, these equations predict extreme curvatures, leading to phenomena that defy common sense, like time slowing down or light being bent. One of general relativity's most surprising predictions is that gravity affects time. Time flows more slowly in stronger gravitational fields. This effect, known as gravitational time dilation, means that time passes more slowly on Earth's surface than it does in space, far from any massive objects. This isn't merely a theoretical concept, it's measurable. Imagine you're wearing a pair of watches, one at your ankle and one on your wrist. Because your ankle is closer to Earth's center, it feels a stronger gravitational pull, and time runs a bit slower there than at your wrist. The difference is tiny but real, and it accumulates over long distances and extreme gravitational fields, such as near a black hole, where time essentially freezes for an outside observer. A century after Einstein published his theory, one of his predictions, gravitational waves, was finally observed. Einstein proposed that massive, accelerating objects, like merging black holes or colliding stars, would create ripples in space-time. These gravitational waves spread outward, like ripples on a pond, carrying energy across the cosmos. In 2015, Scientists at the LIGO Observatory confirmed this prediction by detecting gravitational waves from two merging black holes, a discovery that opened a new era of astrophysics. Gravitational waves allow us to observe cosmic events we previously couldn't, providing a way to listen to the universe's most dramatic collisions. The confirmation of gravitational waves has been one of the most profound validations of general relativity, proving that space-time is not only flexible but can ripple and vibrate. Black holes are perhaps the most extreme manifestations of general relativity. When a star collapses under its own gravity, it can compress into an object so dense that it warps space-time into a point known as a singularity, where density becomes infinite, and the usual laws of physics break down. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. The concept of black holes challenged the boundaries of scientific imagination, but general relativity predicted their existence decades before astronomers observed them. In 2019, the Event Horizon Telescope captured the first-ever image of a black hole's event horizon, confirming yet another aspect of Einstein's theory. Black holes highlight general relativity's power to predict phenomena far beyond human intuition, revealing mysteries that remain largely unsolved even today. It might be tempting to think of general relativity as something distant, affecting only stars and galaxies. But its principles influence technology we use every day. The Global Positioning System, GPS, which relies on satellites orbiting Earth, must account for both special and general relativistic effects to work correctly. Due to both the satellite's speed and their distance from Earth's gravity, their onboard clocks tick slightly faster than clocks on the ground. Without relativistic adjustments, GPS calculations would be inaccurate, placing you miles away from your actual location. This practical application shows that general relativity is not just a theoretical concept, but an integral part of our understanding of reality. It governs everything from cosmic evolution to the precision of modern technology, seamlessly bridging the cosmos with daily life. General relativity doesn't only provide equations, it reshapes our understanding of the universe. By showing that space-time is flexible and interactive, Einstein offered a framework that has inspired generations of physicists and cosmologists to look deeper. General relativity paved the way for our study of black holes, the Big Bang, and even the nature of time itself. Despite its monumental success, general relativity isn't the final answer. At the quantum level, where particles behave unpredictably, general relativity doesn't hold up. The quest to unify general relativity with quantum mechanics into a theory of quantum gravity remains one of the biggest open questions in physics. It's a testament to Einstein's genius that, over a century later, his ideas continue to push us toward new horizons, challenging us to understand the mysteries of space, time, and the very fabric of the cosmos. Quantum Mechanics Basics. Picture a world that doesn't obey the rules we see every day. This is the world of quantum mechanics, where particles can be in multiple places at once, seem to make decisions randomly, and influence each other instantaneously across great distances. Quantum mechanics is the branch of physics that seeks to explain and predict the behavior of particles at the smallest scales. It's the science of the super-small, where particles like electrons and photons reveal surprising and sometimes counterintuitive truths about reality. The quantum world deals with particles smaller than atoms. To get a sense of scale, imagine dividing a single grain of sand in half. Then, keep dividing it until you reach a point where the pieces are no longer even matter as we know it, but fundamental particles like quarks and electrons. Here, traditional physics stops working in expected ways, and new rules take over, rules that defy common logic. One of the first mysteries that quantum mechanics tackled was the dual nature of light and matter. Light, which we see every day as something that helps us navigate our world, behaves as both a wave and a particle. This idea was initially tested through the famous double-slit experiment. In this experiment, light particles, or photons, are fired at a screen with two narrow slits. If we cover one slit, photons behave like tiny pellets, forming a pattern behind the open slit just as you'd expect. But when both slits are open, the photons create an interference pattern, something only waves should produce. Even stranger, if we fire single photons through the double slits one at a time, they still form an interference pattern over time, as if each photon somehow knows about both slits. This dual nature isn't limited to light. Matter itself, like electrons, also shows wave-particle duality. This discovery was one of the first clues that the quantum world behaves in ways far outside our everyday experience. In classical physics, we can measure things with great precision. If we know the speed and position of a car, we can predict exactly where it will be a few seconds later. But quantum mechanics doesn't allow such certainty. Werner Heisenberg's uncertainty principle tells us that we cannot simultaneously know a particle's exact position and momentum with absolute accuracy. The more precisely we measure one, the less precisely we know the other. Imagine trying to grab a bouncing basketball in a dark room. You can hear where it is and make a guess, but you can't pinpoint its exact location and speed at the same time. This uncertainty isn't due to limitations in our measuring tools. It's a fundamental aspect of reality at the quantum level. Particles don't have defined properties until they're measured, and this unpredictability is woven into the fabric of quantum mechanics. One of the most intriguing aspects of quantum mechanics is superposition. Particles like electrons exist in multiple states simultaneously until observed. To make sense of this, physicist Erwin Schrödinger proposed a thought experiment known as Schrödinger's cat. Imagine a cat in a sealed box with a device that has a 50/50th chance of releasing a poison. Until we open the box, the cat is both alive and dead in a superposition of states, much like a quantum particle. Once we look, the state collapses into one outcome, alive or dead. This phenomenon has been proven with particles. Electrons, for example, can be in different places at the same time, a reality we only recognize when we observe or measure them, forcing them to choose one location. The act of measurement in quantum mechanics is like a spotlight. It forces particles to reveal a single outcome from multiple possibilities. Quantum mechanics also reveals that particles can become entangled, meaning their states are linked even if separated by vast distances. If we have two entangled electrons and we measure one, the other instantly reflects this measurement, no matter the distance between them. Albert Einstein famously called this spooky action at a distance, because it seems to defy the speed of light limit. Though it challenges our intuition, entanglement has been confirmed through numerous experiments, suggesting that particles are somehow connected in a way we do not yet fully understand. Entanglement has practical applications in the field of quantum computing and secure communication. Quantum computers use the principles of entanglement and superposition to process data exponentially faster than classical computers for specific types of calculations. Imagine solving a maze with 1,000,000 paths. While a classical computer takes one path at a time, a quantum computer can explore multiple paths simultaneously, dramatically reducing the time needed to find the solution. Unlike classical mechanics, which relies on deterministic outcomes, quantum mechanics is governed by probability. In quantum mechanics, we can only calculate the likelihood of a particle's behavior rather than predict a specific outcome. This probabilistic nature of quantum mechanics implies that we live in a world of chances at the smallest scales. To picture this, imagine rolling a die, but never knowing which number will come up. Quantum mechanics allows you to know the odds, but never the exact result in advance. This probabilistic view challenges the very notion of causality that is foundational to classical physics. While the principles of quantum mechanics may seem remote, they are at the heart of technologies like lasers, MRI machines, and semiconductors. The devices we use every day, from smartphones to computers, rely on the understanding of electrons and photons, which behave according to quantum laws. For instance, the flow of electrons in transistors, tiny switches in electronic circuits, can be explained only by quantum mechanics. Quantum mechanics has shown us that the universe is far stranger than we could have imagined, and we still don't fully understand it. It suggests a world where particles exist in superpositions, where uncertainty is fundamental, and where spooky connections challenge our understanding of reality itself. Despite its mysteries, quantum mechanics has proven to be one of the most successful scientific theories, predicting outcomes with incredible precision. The journey into the quantum world is ongoing, with physicists seeking a unified theory that merges quantum mechanics with Einstein's general relativity, a goal that could finally offer a comprehensive view of the universe. Quantum mechanics invites us to think beyond the limits of common experience, to see the universe as not just particles and waves, but as a complex, interconnected web of probabilities that continually reshape our understanding of reality. The uncertainty principle. Imagine you're trying to catch a bouncing rubber ball in a dark room. You can't see it, but you hear it hit different parts of the room. You reach out, guessing where it might be, but every time you try to catch it, it changes direction. In quantum mechanics, particles act a lot like that bouncing ball, except it's not just your vision that's blocked. There's a fundamental rule in nature preventing you from knowing certain things about the particle at the same time. This concept is called the uncertainty principle, first proposed by physicist Werner Heisenberg in 1927. The uncertainty principle suggests that at a fundamental level, there is a limit to how precisely we can know certain pairs of properties about a particle, specifically its position and momentum. In other words, the more precisely we try to know a particle's location, the less we know about its momentum, and vice versa. This isn't about imperfect tools or methods. It's a fundamental property of the quantum world. To understand the uncertainty principle, think of a particle like an electron as a cloud of probabilities. In classical physics, we imagine particles like marbles. They have specific positions and velocities at any given time. However, in quantum mechanics, particles don't have exact locations until they're measured. Before measurement, they exist in a superposition of all possible positions and momentums, like a blurred photograph where nothing is fully clear. When we measure a particle's position very precisely, we effectively collapse its probability wave, forcing it to choose a specific location. But in doing so, we lose information about its momentum. If we try to measure the particle's momentum with high precision, we end up with less information about where it is. Unlike in the macro world, where limitations in measurement can often be solved with better tools, the uncertainty principle isn't due to technological limitations. It's built into the structure of quantum systems. When we measure a particle in quantum mechanics, we interact with it, typically by hitting it with photons or some form of energy. This act of measurement disturbs the particle, changing its properties. For instance, to measure a particle's position precisely, we might use high-energy photons. However, high-energy photons alter the particle's momentum, meaning the more accurately we locate it, the less precisely we know its speed and direction, so even our best efforts at precision run up against this fundamental barrier, a characteristic of all quantum particles. The uncertainty principle isn't just an oddity. It has far-reaching implications. It implies that the very notion of a deterministic universe, one where future events are entirely predictable from past ones, doesn't apply at the quantum level. Quantum systems behave probabilistically, and this principle is the core reason why. The path of an electron around an atomic nucleus, for example, cannot be described as a neat orbit like planets around the sun. Instead, electrons exist in clouds of probability around the nucleus, where they are likely to be found. The principle also affects the energy levels within atoms. Since particles have a degree of uncertainty in their position and momentum, they cannot have zero energy. There's always a minimum amount of zero-point energy inherent in all particles. This is why atoms remain stable and don't collapse, as the uncertainty in an electron's position and energy keeps it from falling into the nucleus. One of the most fascinating phenomena that emerges from the uncertainty principle is quantum tunneling. Imagine a ball rolling up a hill. In classical mechanics, if the ball doesn't have enough energy, it will roll back down. But in the quantum world, particles can tunnel through barriers they seemingly lack the energy to cross, thanks to the uncertainty in their position and energy. Quantum tunneling is a crucial process in nuclear fusion in stars and forms the basis of modern technologies, like the transistors in computers. The uncertainty principle is challenging because it defies our everyday experience. It forces us to rethink what it means for something to exist with specific properties. In our daily lives, we expect objects to have well-defined positions and velocities, like cars on a highway or planets in orbit. Quantum mechanics and the uncertainty principle in particular reveal that, on the smallest scales, reality isn't as concrete. Particles are both here and there, fast and slow, clear and blurred all at once. Werner Heisenberg's principle reshaped physics, inspiring debates about the nature of reality itself. In fact, it led to the development of the Copenhagen interpretation of quantum mechanics, which suggests that particles exist as probabilities until measured. This interpretation essentially says that measurement shapes reality, that particles choose a state when observed, an idea that still prompts philosophical and scientific debate today. The uncertainty principle has redefined how we understand the limits of knowledge in physics. It shows that uncertainty is not a flaw in our understanding or our technology, but a built-in feature of the universe. At the quantum level, particles are not like marbles. They are like waves, fields of possibilities that collapse only when we observe them. This principle isn't a problem to be fixed. It's a fundamental aspect of how the universe operates, giving rise to the complex, fascinating behaviors of quantum systems. So, when we look at the uncertainty principle, we are not just learning about the limitations of measurement, but uncovering a deeper truth about the fabric of reality. A universe where, at its most fundamental level, nature is as much about the unknown as it is about what can be known. Quantum entanglement. Imagine two identical twins separated at birth. Years later, each goes on to live a very different life, one in a bustling city, the other on a quiet island. Now, imagine that no matter the distance, each twin somehow feels what the other experiences, as if there's a mysterious thread connecting their lives. This idea captures the essence of quantum entanglement, a phenomenon so strange that Albert Einstein famously called it spooky action at a distance. Quantum entanglement is a principle that describes how particles, once entangled, become deeply linked, such that the properties of one instantaneously influence the properties of the other, even if separated by vast distances. In the quantum world, if two particles are entangled, measuring one particle's state reveals the state of the other instantly, no matter how far apart they are. This concept strikes at the core of quantum mechanics and challenges our most fundamental understanding of space, time, and causality. To understand entanglement, let's start with particles in a special quantum state. In classical physics, we can easily measure properties like position, velocity, or spin for each object individually, but in quantum mechanics, particles can exist in a superposition, where they simultaneously hold multiple states at once, sort of like a coin that is both heads and tails until we look at it. Now, suppose two particles, say two electrons, are created together in such a way that they become entangled. Electrons have a property called spin, which can be imagined as a type of rotation and is often measured as spin up or spin down. When entangled, the electron spins become correlated in a way that, even if they're separated by galaxies, knowing the spin of one particle automatically tells you the spin of the other. If you measure one particle and find it is spin up, the other, no matter how far away, will instantly be found to be spin down. The particles are like quantum twins. They share a state that is intertwined. One of the most mystifying aspects of entanglement is that it appears to defy the speed of light. which according to Einstein's theory of relativity is the ultimate speed limit. If two entangled particles are on opposite ends of the universe, measuring one instantly affects the other. This seems to suggest that information somehow travels faster than light between them. But in quantum mechanics, entanglement doesn't rely on traditional communication between particles. It's not that one particle is sending a signal to the other. Rather, their states are interdependent from the moment of entanglement. Think of it as if both particles are sharing a single unified wave function, a mathematical description of their quantum state. When you measure one, the entire wave function collapses, meaning the state of the entire system becomes known instantaneously. This strange property of entanglement was famously challenged by Einstein, Boris Podolsky, and Nathan Rosen in 1935, who argued that quantum mechanics might be incomplete. They proposed what's now known as the EPR paradox, suggesting that if quantum mechanics allowed for that everything we perceive in 3 dimensions may be encoded on a 2-dimensional surface, much like a hologram. The concept, although abstract, arose from a pressing problem in theoretical physics that involved black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking noticed a peculiar relationship between black holes and entropy, the measure of disorder or information contained in a system. Bekenstein proposed that the entropy of a black hole isn't proportional to its volume, as one might expect, but instead to the area of its event horizon, the boundary beyond which nothing can escape. This discovery was shocking, because it suggested that the information describing everything that falls into a black hole could be encoded on its surface area, not its volume. This is where the holographic principle begins to emerge. In the 1990s, the physicist Leonard Susskind and others took this idea further. They proposed that the same principle that applies to black holes might apply to the entire universe. In other words, all the information in our seemingly 3-dimensional universe could be encoded on a distant 2-dimensional boundary, much like how a hologram stores a 3D image on a flat surface. Just as a hologram creates the illusion of depth, our universe might be an illusion of 3 dimensions projected from a lower dimensional reality. This idea is deeply tied to string theory, one of the leading candidates for a theory of everything. String theory attempts to describe the fundamental constituents of the universe not as point-like particles, but as tiny vibrating strings. In certain versions of string theory, the holographic principle naturally arises as a feature of the theory. In this framework, space and time themselves are emergent properties woven together from more fundamental, lower-dimensional information. The implications of the holographic principle are profound and perplexing. If our universe is a projection from a lower-dimensional realm, it challenges our very understanding of what it means to exist in space and time. The objects we perceive as solid and real may be at their core an encoded representation on a distant cosmic boundary. But does this mean our everyday experiences are merely illusions? Not exactly. Much like a hologram provides a realistic representation of an object, the 3-dimensional world we navigate feels real because the encoded information is so richly detailed. The atoms that make up our bodies and the stars in the sky may be encoded on a cosmic boundary, but they still behave according to the laws of physics we observe in our familiar everyday world. One of the most exciting aspects of the holographic principle is that it could provide a framework for resolving some of the biggest puzzles in physics. In particular, it offers a possible solution to the long-standing conflict between quantum mechanics, the theory that governs the very small and general relativity, the theory that governs the very large. By viewing space-time itself as an emergent property from a more fundamental holographic description, the principle hints at a deeper unity between these two pillars of physics. While experimental confirmation of the holographic principle remains elusive, its theoretical foundation is robust, and physicists continue to explore its implications. For example, in 2017, researchers discovered hints of holographic duality in simple models of quantum entanglement, providing indirect support for the principle. Additionally, tools from holography have been used to study the behavior of quantum systems, giving rise to new insights into both condensed matter physics and the nature of gravity. In conclusion, the holographic principle stands as one of the most profound and speculative ideas in modern physics. It challenges our fundamental understanding of reality, suggesting that the universe we experience may be a projection from a lower dimensional boundary. While the idea remains largely theoretical, its potential to unlock deeper insights into the nature of space, time, and information continues to inspire physicists to push the boundaries of human knowledge. Whether or not the holographic principle turns out to be a true description of the universe, it offers a tantalizing glimpse into the depths of the unknown, reminding us that reality is often stranger than we can imagine. The multiverse theory. The multiverse theory suggests that our universe is just one of countless others, each with its own set of laws, dimensions, and properties. Imagine this. What if, instead of just one universe that arose from the Big Bang, there are many, perhaps an infinite number, each with its own version of reality, its own physics, and perhaps even its own versions of us? This idea forms the basis of multiverse theory, one of the most fascinating and speculative concepts in modern physics. The multiverse theory isn't just a recent science fiction idea, it has roots in the study of cosmology and quantum mechanics. In the early 20th century, physicists like Hugh Everett and Niels Bohr struggled with the strange behavior of particles at the quantum level. When you observe a particle, it seems to choose one state, but before observation, it can exist in multiple states simultaneously, a concept known as superposition. Hugh Everett took this concept further with his many worlds interpretation, suggesting that when a particle takes on one of its many possible states, all other possibilities also occur, but in separate, parallel universes. From there, the multiverse theory grew, fed by developments in cosmology, string theory, and theoretical physics. Today, physicists explore the idea of the multiverse in various ways, each suggesting a unique mechanism that could produce multiple universes. There isn't just one way to imagine a multiverse. There are actually several main types proposed by physicists. Each brings its own perspective on how these alternate realities might come to exist: bubble universes or eternal inflation. Imagine that the Big Bang wasn't a unique event. In this version of the multiverse theory, space is like an inflating balloon, and within this ever-expanding cosmic bubble, smaller bubbles continuously form. Each bubble represents a separate universe with its own physical properties, separate from ours. Some might have entirely different laws of physics, others might be quite similar. This concept comes from inflation theory, which describes the rapid expansion of space in the early universe. Alan Guth and André Lande, pioneers of this idea, suggested that inflation might not end uniformly across space, but instead create patches or bubbles, each becoming its own universe. The many worlds interpretation. Rooted in quantum mechanics, this theory suggests that every time a quantum decision is made, every time a particle has multiple paths it can take, the universe splits to accommodate each outcome. For example, if you're faced with a decision, each possible choice might exist in a different universe. This interpretation suggests that there are infinite versions of you, making every possible decision in every possible way, each leading to a different universe. The many worlds interpretation is one of the most popular in pop culture, often imagined as a kind of cosmic branching tree of choices and events. The brain multiverse. In string theory, our universe might be a brain floating within a higher dimensional space known as the bulk. Other brains could coexist in the bulk, representing parallel universes just a small distance away in higher dimensional space. If these brains occasionally interact or collide, it might even explain phenomena like the Big Bang. Mathematical multiverse. Physicist Max Tegmark proposed that all possible mathematical structures exist in their own universes. In this view, mathematical equations and physical laws define realities, and each set of these mathematical rules could describe its own universe. In this mathematical multiverse, any structure that can exist mathematically does exist as a separate reality. Imagine a vast library with endless aisles. Each book on the shelves tells a different story, yet all are variations on certain themes. Some books contain stories almost identical to the one you're living now, while others diverge wildly. Some are tales of universes where stars are different colors, where gravity works differently, or where life never developed at all. This library represents the multiverse. Each book is a self-contained universe with its own narrative. Each is real as the others, but with its own unique properties. Another analogy might be the surface of a pond with countless bubbles forming and popping. If each bubble is a universe, some form and grow, developing into full-fledged cosmoses with galaxies and stars. Others might collapse before reaching a mature state, while still others continue to float along, coexisting yet never touching. The multiverse theory isn't just a whimsical idea. It offers potential answers to some of the biggest questions in physics. One major question is why our universe's conditions are just right for life. Physicists call this the fine-tuning problem. The constants that define our universe, like the strength of gravity or the speed of light, appear to be tuned precisely to allow stars, planets, and life to form. If any of these constants were slightly different, life as we know it wouldn't exist. The multiverse theory provides an explanation for this fine-tuning. In an infinite sea of universes, each with different constants, it's not surprising that some would happen to have conditions favorable for life. We just happen to be in one of those universes. The multiverse theory remains highly speculative, and testing it presents a significant challenge. By definition, other universes are separate from ours and might be undetectable. However, scientists are exploring potential indirect evidence. Some hypothesize that gravitational waves or cosmic background radiation might show traces of interactions between our universe and others. Others suggest that experiments in quantum mechanics might eventually offer clues supporting the many worlds interpretation. Still, proving the multiverse's existence is a daunting task. For now, the multiverse remains a thrilling frontier, an idea that pushes the boundaries of what science can address. Whether real or imaginary, the multiverse expands our sense of possibility, suggesting that reality may be far vaster and more varied than we ever thought. The multiverse theory invites us to imagine an endless tapestry of realities, each with its own unique version of physics, existence, and perhaps even consciousness. Whether or not we ever prove its existence, the concept of the multiverse reminds us of the depth and mystery inherent in the cosmos, and that just beyond our visible horizon, there may lie an infinity of unknown worlds waiting to be discovered. The many worlds interpretation. The many worlds interpretation, MWI, of quantum mechanics is one of the most mind-expanding and radical ideas in modern physics. It suggests that every time a quantum event occurs, such as the decay of a radioactive particle, the path a photon takes, or the spin of an electron, the universe splits into multiple, parallel versions of itself. In each of these universes, different outcomes of that quantum event play out. Rather than a single reality where only one outcome occurs, the many worlds interpretation posits that all possible outcomes actually happen, but in separate coexisting worlds. To understand how MWI works, it's useful to begin with the problem it tries to solve, the famous paradox of quantum superposition. According to quantum mechanics, particles like electrons can exist in multiple states simultaneously. For example, an electron can be in a state of both spin up and spin down at the same time. This is called superposition. The puzzling part arises when we try to observe the particle. As soon as we make a measurement, the particle seems to collapse into one definite state, either spin up or spin down, but not both. Why does this collapse happen, and what causes the universe to choose one particular outcome over another? The traditional interpretation of quantum mechanics, known as the Copenhagen interpretation, claims that the act of measurement forces the system to collapse into one state, and this collapse is instantaneous and random. But this explanation is unsatisfying to many physicists. It introduces an element of randomness that feels arbitrary and doesn't explain what happens to the other possibilities, the ones that didn't occur in our universe. This is where the many worlds interpretation comes in, proposed by physicist Hugh Everett in 1957. Everett's idea was that the collapse never really happens. Instead, when a quantum event takes place, all possible outcomes occur, but in different branches of the universe. For instance, if you flip a quantum coin, it doesn't just land heads or tails. Both heads and tails happen, but in different universes. In one universe, you see heads, while in another, your counterpart sees tails. Imagine standing at a crossroads with two paths in front of you. In our everyday world, you can only choose one path. But in the quantum world of the many worlds interpretation, you take both paths, each in a different branch of the universe. From your perspective, you've made only one choice, but another version of you exists in the other universe, having made the opposite choice. The implications of this are staggering. If the many worlds interpretation is correct, then every quantum event, down to the smallest interactions at the atomic level, creates a branching of universes. This means there could be an almost infinite number of parallel realities, with every possible configuration of events playing out somewhere. In some universes, you might have chosen a different career or met different people. In others, entire galaxies might have formed differently, and the laws of nature might not even resemble those in our universe. One way to grasp the sheer scope of this idea is through Schrödinger's cat, a famous thought experiment in quantum mechanics. In the experiment, a cat is placed in a box with a quantum mechanism that has a 50% chance of killing the cat or keeping it alive. Until the box is opened, the cat is said to be in a superposition of both dead and alive. In the Copenhagen interpretation, when you open the box, the superposition collapses, and the cat is revealed to be either dead or alive. But according to the many worlds interpretation, there is no collapse. Instead, when you open the box, the universe splits into two. In one universe, the cat is dead, and in the other, it is alive. Both outcomes occur, but you, the observer, only experience one of them. Another version of you exists in the parallel universe, observing the opposite outcome. This may seem fantastical, but the many worlds interpretation has a certain elegance in its simplicity. It avoids the need for arbitrary collapse mechanisms or special observers who somehow cause quantum systems to choose one reality over another. Instead, MWI treats the entire universe, including observers, as part of the same quantum system, all governed by the same physical laws. In this view, the universe is constantly branching, creating an enormous multiverse of realities. Despite its radical nature, MWI is still a highly debated interpretation. Critics argue that it introduces too many unobservable realities, making it difficult to test or falsify. If these parallel universes are forever separated from our own, how can we ever know they exist? Additionally, some philosophers and physicists feel uneasy about the idea that every possible event happens somewhere, as it seems to strip meaning from choices and consequences. If every possible outcome occurs, does it matter what we do? However, supporters of the many worlds interpretation argue that it provides a natural solution to the mysteries of quantum mechanics without introducing new, unexplained processes. From their perspective, the universe is already much stranger than we imagined, and MWI simply takes quantum mechanics to its logical conclusion. It also has intriguing implications for other fields such as cosmology and black hole physics, where the concept of multiple realities could offer new insights into the structure of space and time. In the end, the many worlds interpretation pushes us to reconsider our understanding of reality. If every possible version of the universe exists somewhere, what does that mean for our sense of identity, free will, and existence itself? While we may never fully know if we inhabit one of countless parallel worlds, the exploration of these ideas stretches the boundaries of human imagination and forces us to confront the deepest mysteries of the cosmos. Quantum gravity. Imagine you're holding a grain of sand in your hand, a tiny object yet part of the vastness of a beach. Now zoom in closer, way closer, down to the atomic level, where matter breaks into molecules, then atoms, and then even smaller particles like protons and electrons. Eventually, you reach the realm of quantum mechanics, where the world behaves in ways that seem strange and alien compared to our everyday experience. But what if we zoom out again, this time far beyond the beach, beyond the planet, to the scale of galaxies and black holes, where gravity dominates and space-time itself bends and warps? These two perspectives, quantum mechanics and general relativity, are the most successful theories in physics. Quantum mechanics governs the smallest scales, explaining the behavior of particles and the fundamental forces, except gravity. On the other hand, Einstein's theory of general relativity describes how gravity works on the large scale, showing that massive objects like planets and stars curve space-time, and it is this curvature that we perceive as gravity. Each theory works brilliantly in its respective domain, but when it comes to combining the two into a single framework, a theory of quantum gravity, we hit a wall. Quantum gravity is the attempt to reconcile these two seemingly incompatible theories, and it has proven to be one of the greatest unsolved puzzles in modern physics. It's like trying to merge two languages that have completely different grammars. One is probabilistic and deals with discrete particles, while the other is deterministic and continuous, describing smooth curves of space-time. To understand why merging them is such a challenge, let's first unpack what each theory tells us about reality. At the quantum level, reality is governed by uncertainty. Particles like electrons don't have definite locations until we observe them. Instead, they exist in a cloud of probabilities, where they could be in several places at once. Forces, like electromagnetism, are carried by particles called force carriers such as photons. The theory of quantum field theory, QFT, extends this idea, treating particles as excitations in underlying fields that exist throughout space. These fields are what dictate the behavior of particles in the quantum world. However, gravity doesn't quite fit into this picture. According to general relativity, gravity isn't a force in the traditional sense. It's a feature of the fabric of space and time. Massive objects curve space-time, and this curvature tells other objects how to move. A planet orbits the sun not because an invisible force is pulling on it, but because the sun's mass curves the space around it, and the planet follows that curved path. But in the quantum world, where particles move in discrete steps and fields are the fundamental building blocks, this smooth, continuous description of space-time becomes problematic. If we try to treat gravity like the other fundamental forces, such as electromagnetism or the strong nuclear force, we run into a paradox. When we zoom in on space-time to the smallest scales, called the Planck scale, the smooth fabric of space-time becomes grainy and erratic, like the foamy crest of a turbulent ocean wave. At these scales, general relativity breaks down, and we need a quantum theory of gravity to describe what's really happening. The search for quantum gravity is not just about solving an academic puzzle. It's essential for understanding some of the most extreme phenomena in the universe, such as black holes and the Big Bang. In these situations, the pull of gravity becomes so strong and the scale so small that both quantum mechanics and general relativity should apply simultaneously. But right now, we don't have a working theory that can handle both. One of the biggest challenges in creating a theory of quantum gravity is renormalization. In quantum field theory, when calculating interactions between particles, we sometimes get nonsensical infinite results. But physicists have developed techniques to cancel out these infinities, allowing us to get meaningful answers. When we try to apply these same techniques to gravity, though, the infinities don't cancel out. Gravity resists being tamed by the methods that work so well for other forces. There are several competing ideas for how to develop a theory of quantum gravity, with two of the most prominent being string theory and loop quantum gravity. String theory posits that instead of being point-like particles, the fundamental building blocks of reality are tiny vibrating strings. These strings can vibrate in different ways, and the different vibrational modes correspond to different particles. String theory also introduces extra dimensions beyond the familiar 3 of space and 1 of time. There could be as many as 11 dimensions, though they are hidden from view at the scales we typically observe. In string theory, gravity is explained by the existence of a particle, called the graviton, which mediates the gravitational force. The theory provides a framework for unifying all fundamental forces, including gravity, under one mathematical roof. However, it remains speculative, as its predictions have yet to be experimentally verified. Loop quantum gravity, on the other hand, takes a more conservative approach. It suggests that space-time itself is not continuous, but is made up of tiny loops, woven together like a fabric. These loops are incredibly small, on the order of the Planck scale, and they form the fundamental building blocks of space-time. This theory avoids the infinities that plague attempts to quantize gravity using traditional methods, offering a possible path forward. However, loop quantum gravity, like string theory, is still incomplete and lacks direct experimental evidence. Understanding quantum gravity isn't just about solving a technical problem in physics, it's about unlocking a deeper understanding of the universe. The universe, at its most fundamental level, may not be what we perceive it to be. In fact, the very fabric of space and time might behave differently than we expect. Quantum gravity might reveal new insights into the nature of black holes, the beginning of the universe, and even the fundamental structure of reality. Just as quantum mechanics revolutionized our understanding of the microscopic world and general relativity reshaped our view of the cosmos, the successful development of quantum gravity could be the key to the next great leap in physics, one that ties together all of reality's scales from the tiniest particles to the largest galaxies into a coherent picture. It's a quest to understand the deep interplay between the smallest building blocks of nature and the vast cosmic forces that govern the universe. Anthropic principle. The anthropic principle is one of those philosophical and scientific ideas that quietly reshapes how we think about the universe and our place within it. On the surface, it asks a deceptively simple question: why does the universe appear to be so perfectly tuned for life, and in particular human life? Dig deeper, and it forces us to confront profound questions about the nature of existence, cosmology, and the role of consciousness in the universe. At its core, the anthropic principle is about explaining the apparent fine-tuning of the universe. When we observe the physical constants and laws of nature, things like the strength of gravity, the charge of the electron, or the expansion rate of the universe, we notice so that they fall within very narrow ranges that allow life, at least life as we know it, to exist. If any of these constants were even slightly different, the universe could have been a vastly different place, one where galaxies, stars, planets, and life could not form. Let's put it into a simple analogy. Imagine you walk into a room where a giant roulette wheel is spinning. The wheel has millions of tiny slots, each corresponding to a different set of physical laws and constants. As the wheel slows down, it lands precisely on one of the slots that allows for life. The question the anthropic principle raises is it just a lucky coincidence that the wheel stopped on a life-permitting slot, or is there something deeper at work? There are two major formulations of the anthropic principle: the weak anthropic principle and the strong anthropic principle. The weak anthropic principle, WAP, is in some sense the least controversial. It simply states that we shouldn't be surprised that we observe a universe fine-tuned for life, because if the universe weren't suited for life, we wouldn't be here to observe it. In other words, the conditions of the universe must allow for the observer's existence. It's a tautology. Life exists in the universe because the universe allows life to exist. For example, imagine you're standing on Earth, marveling at how it's the perfect distance from the sun to support life. According to the weak anthropic principle, this is not a surprising observation because if Earth weren't in this Goldilocks zone, not too hot, not too cold, you wouldn't be standing there thinking about it. This formulation of the principle is sometimes seen as more of a clarification than an explanation, but it still has important implications. It reminds us that our perspective as observers is necessarily biased. We can only observe conditions compatible with our existence. The strong anthropic principle, SAP, on the other hand, takes things a step further. It suggests that the universe must have the properties that allow life to develop. In other words, the universe is not just randomly fine-tuned for life, it is somehow compelled to be that way. The SAP opens the door to a more teleological view of the cosmos, hinting that life, and maybe even consciousness, is not just a fortunate accident, but an integral part of the universe's structure. Some proponents of the strong anthropic principle argue that life is the universe's way of knowing itself. From this perspective, human consciousness and intelligence are not just side effects of cosmic evolution, but central features of the universe's design. In this sense, the anthropic principle doesn't just explain why the universe supports life. It raises the possibility that life and consciousness are the ultimate goals of the universe. Now, one of the most interesting implications of the anthropic principle is how it intersects with the idea of the multiverse. If we imagine that our universe is just one of a potentially infinite number of universes in a vast multiverse, then the fine-tuning problem becomes less mysterious. In a multiverse with every possible set of physical laws and constants, there would inevitably be at least some universes where the conditions are just right for life. The fact that we happen to live in one of those universes is no more surprising than finding yourself living on a planet like Earth. It had to be this way for us to exist. To illustrate, let's return to the roulette wheel analogy. Imagine instead of just one wheel, there are countless wheels, each corresponding to a different universe. Some wheels land on universes where life is impossible, where gravity is too weak, or the cosmological constant is too strong, causing the universe to tear apart before galaxies can form. But some wheels land on universes where the conditions are just right. In a multiverse with infinite rolls of the dice, the odds of at least one life-permitting universe being realized are inevitable. However, not everyone is satisfied with the multiverse explanation. Some argue that invoking a multiverse to explain the fine-tuning of our universe is like explaining one mystery by introducing an even bigger one. After all, how do we prove that a multiverse exists? Moreover, the strong anthropic principle still lingers in the background, suggesting that perhaps the universe is designed for life in a more fundamental way, whether or not there are multiple universes. Philosophically, the anthropic principle touches on the age-old debate between randomness and purpose. Is the universe just a random, purposeless accident where life is an unlikely but inevitable outcome in one of countless possible universes? Or is there a deeper reason why the universe is the way it is, something that points to purpose, design, or even consciousness being woven into the fabric of reality? In summary, the anthropic principle asks why the universe seems so perfectly calibrated for life, whether you interpret it through the lens of the weak anthropic principle, where life is simply a product of the conditions we can observe, or through the strong anthropic principle, which hints at deeper cosmic intent. The principle challenges us to rethink our place in the universe. When combined with the idea of a multiverse or theories that emphasize consciousness as central to reality, the anthropic principle becomes not just a scientific question, but a profound philosophical inquiry into the nature of existence itself. The information paradox. The information paradox is one of the most intriguing mysteries in theoretical physics, sitting at the crossroads of quantum mechanics and general relativity. To understand why it's such a puzzling concept, imagine a library that holds every book, every thought, and every experience in the universe. Now imagine a fire sweeping through it, burning every page into oblivion. What happens to the information contained in those books? Does it cease to exist entirely, or does some trace of it remain? The same question applies to black holes, the cosmic giants known for their immense gravitational pull. They devour anything that crosses their event horizon, light, matter, and information alike. But according to quantum mechanics, information, in a strict sense, can never be destroyed. This conflict between theories brings us to the heart of the information paradox. To begin, let's clarify what it means for information to be lost. In physics, information about the state of a particle, like its position, momentum, and properties, allows us to know where it's been and predict where it might go. Quantum mechanics asserts that information about a system's initial state is always preserved, even if it's scrambled beyond recognition. This principle is known as unitarity and is foundational to quantum theory. Black holes, however, seem to defy this rule. Imagine tossing a book into a black hole. As it crosses the event horizon, the boundary from which nothing can escape, it's pulled into a dense, singular point at the black hole's core. From the outside, the information in the book seems to disappear forever. Eventually, though, black holes emit Hawking radiation, a faint energy glow theorized by physicist Stephen Hawking in 1974. Over time, as the black hole emits this radiation, it loses mass and will eventually evaporate completely. When it's gone, the information about the book you threw in seems to be erased from the universe forever. But here's the dilemma. If quantum mechanics is correct, the information within that black hole should somehow survive. Yet if general relativity is correct, it would be gone without a trace. This is the essence of the information paradox. Two fundamental pillars of physics appear to be in direct conflict. Stephen Hawking's work on black hole thermodynamics and the nature of black hole radiation was groundbreaking, because it implied that black holes are not entirely black. They emit radiation, meaning they slowly lose energy and mass. This emission process, though, didn't seem to carry any information about what the black hole had consumed. Whether it swallowed a star or a teaspoon of antimatter, the radiation appeared identical, as if every detail about what fell into the black hole was lost. To understand the gravity of this implication, consider a jigsaw puzzle. If you burn it to ashes, you can no longer see the image, but the physical puzzle pieces once existed and carried the pattern that made up the image. In quantum mechanics, however, this pattern should be traceable even in the ashes. Hawking's work seemed to suggest otherwise. It implied that once a black hole evaporated, the puzzle pieces were gone for good. Physicists have wrestled with the information paradox for decades, proposing multiple solutions. Here are a few of the most prominent theories. The holographic principle. One of the most famous approaches involves the idea that all the information about what falls into a black hole is stored on its event horizon in a two-dimensional form, like a hologram. This theory, initially proposed by Gerard Hooft and expanded by Leonard Susskind, suggests that the black hole's surface can contain all the information about the objects inside. It's akin to how a hologram holds three-dimensional information on a two-dimensional surface. According to this principle, the information isn't lost, but encoded on the black hole's surface, preserving unitarity, the firewall hypothesis. Another possible answer, though still contentious, is that a firewall exists at the event horizon. When an object falls into the black hole, it hits this firewall and is incinerated. This would create a barrier that somehow encodes information, but would require breaking a principle of general relativity, smooth space-time at the event horizon. Physicists like Don Page and Raphael Bousso have worked on variations of this idea, although it remains controversial because it challenges our understanding of relativity. Quantum entanglement and information leakage. Some researchers believe that quantum entanglement might hold the key to the puzzle. The idea is that particles falling into a black hole are entangled with particles on the outside. When Hawking radiation is emitted, these particles might carry information in an encoded form, subtly leaking the information back into the universe. Physicists studying the concept of entanglement entropy think it may reveal how information escapes from a black hole over time without contradicting quantum mechanics. Wormholes and ER equal sign, EPR, proposed by physicists like Juan Maldacena. The ER equal sign EPR conjecture suggests a connection between two seemingly different phenomena: Einstein-Rosen bridges, wormholes, and entangled particles, EPR pairs. In this theory, entangled particles outside a black hole might be connected by wormholes to particles inside, forming a bridge through which information can pass, though this is still speculative. The information paradox isn't just a black hole problem. It challenges the compatibility of general relativity and quantum mechanics, the two cornerstones of modern physics. Each theory is brilliantly successful within its own domain. Quantum mechanics explains the subatomic world, while general relativity governs the large-scale structure of the universe. But black holes bring these two realms together in a way that defies reconciliation, exposing potential gaps in our understanding. Resolving the information paradox could lead to a deeper theory of quantum gravity, a framework that unites quantum mechanics and general relativity. Such a breakthrough might reshape our understanding of the universe at the most fundamental level, offering insights into everything from the nature of time and space to the fabric of reality itself. The information paradox remains unsolved, but it fuels some of the most ambitious theories in physics. As physicists continue exploring this mystery, they're driven by the possibility that somewhere in the clash between quantum mechanics and relativity lies the blueprint for a new, more complete understanding of reality. The black hole firewall hypothesis. The black hole firewall hypothesis is one of the most daring proposals in theoretical physics, an idea that challenges both our understanding of black holes and the laws of physics as we know them. It suggests that a firewall of incredibly high-energy particles could exist at the event horizon of a black hole, potentially obliterating anything that falls in. To understand why this hypothesis arose, we need to explore what it implies about black holes and why some physicists think it may be a solution to one of the biggest paradoxes in modern science. To get to the heart of the firewall hypothesis, let's imagine a person approaching a black hole, often called an astronaut, in thought experiments. According to Einstein's theory of general relativity, the astronaut would experience something called gravitational time dilation as they near the black hole's event horizon, which is the boundary beyond which nothing, not even light, can escape. The closer they get to the event horizon, the slower time would appear to move for them from the perspective of an outside observer. At the event horizon itself, time would seem to freeze for the astronaut, and in theory, they could fall right through the event horizon without noticing anything unusual, until they get crushed by the immense gravity closer to the black hole's core. But quantum mechanics, which describes the behavior of particles on the smallest scales, adds a complication. Quantum theory holds that information about particles cannot simply disappear. It has to go somewhere. When black holes evaporate and eventually disappear through Hawking radiation, a theoretical process proposed by Stephen Hawking where black holes emit faint radiation and lose mass over time, it would seem that the information about everything that fell into the black hole also vanishes. This contradiction between quantum mechanics and general relativity is known as the black hole information paradox. The firewall hypothesis is one of the proposed resolutions to this paradox. It suggests that, instead of smoothly crossing the event horizon, anything falling into a black hole would hit a firewall and be incinerated. This violent outcome would mean that information about the particles falling into the black hole isn't lost, as it never actually crosses the event horizon to begin with. It's somehow preserved in the intense radiation at the boundary. The idea of a firewall sounds extreme, even strange, but here's a relatable analogy. Imagine that you're approaching the door to a vault that leads to a room with all sorts of secrets, perhaps a room that symbolizes the unknown beyond the event horizon. As you step closer, a security system triggers a blinding, searing wall of lasers at the doorway, preventing you from entering and incinerating everything you carry. While dramatic, the firewall acts like a safeguard, ensuring that whatever crosses the boundary, in this case you, is immediately reduced to information in the form of energy or particles. In this hypothesis, the firewall at a black hole's event horizon functions similarly to that laser security system. It's a barrier that burns up particles and potentially even large objects upon impact. From this perspective, the firewall encodes the information by annihilating it at the horizon, so no actual crossing of the event horizon ever occurs. If the firewall hypothesis sounds radical, that's because it is. It challenges some fundamental ideas in physics. For one, general relativity holds that space-time is smooth and continuous. This continuity means that for a sufficiently large black hole, someone falling through the event horizon wouldn't feel any immediate difference, what physicists call the principle of no drama at the horizon. However, the firewall hypothesis shatters this notion of a smooth passage. If a firewall exists, anyone approaching the black hole wouldn't just feel the pull of gravity. They'd encounter an intense wall of energy that destroys them before they even reach the interior. Another conflict arises with the equivalence principle, one of the foundations of general relativity, which states that the laws of physics are the same for an observer in freefall as for one in uniform motion. If the firewall exists, then falling into a black hole is a unique experience that differs from other forms of freefall, suggesting that the equivalence principle may not hold at the event horizon. The firewall hypothesis is still a topic of heated debate in the scientific community. Many physicists are exploring alternative solutions to the information paradox that don't require breaking the equivalence principle. Some propose that the information is encoded in the Hawking radiation itself, which could carry information about particles in a subtle way that preserves it without requiring a firewall. Others suggest that we might need a new theory that merges quantum mechanics and general relativity more harmoniously. The firewall hypothesis could be a placeholder, a way of acknowledging that our current theories don't fully reconcile the mysteries of black holes. It suggests that, in the intense and chaotic environment of a black hole, our usual rules about the behavior of information and matter may need to be revised. In the end, the black hole firewall hypothesis serves as a striking example of the questions physicists are wrestling with as they push the boundaries of our understanding. Whether or not firewalls are real, they highlight the ways in which black holes challenge our grasp of reality itself, revealing how much we still have to learn about the universe's most enigmatic phenomena. The Wheeler-DeWitt equation. The Wheeler-DeWitt equation is often called the wave function of the universe and is one of the most intriguing concepts in theoretical physics. Proposed in the 1960s by physicists John Wheeler and Bryce DeWitt, the equation attempts to unify quantum mechanics and general relativity, a quest to describe the nature of the universe in a single, consistent framework. This equation stands out because, unlike other equations in physics, it doesn't seem to involve time at all, raising the question, does time as we know it exist at the most fundamental level? Imagine that our understanding of the universe is like a giant puzzle with two massive sections. On one side, we have general relativity, which describes the large-scale structure of the universe, the movements of stars, galaxies, and the fabric of space-time itself. On the other side, we have quantum mechanics, which rules over the microscopic world of particles, where uncertainty and probabilities dominate. These two theories work beautifully within their own domains, but clash when we try to use them together, particularly when describing extreme conditions like the birth of the universe or the insides of black holes. Physicists believe that a unified theory would combine these domains, but to do this they need an equation that incorporates the mechanics of both gravity, as described by relativity, and quantum effects. The Wheeler-DeWitt equation was one of the first attempts at this type of synthesis. In simple terms, it seeks to describe the quantum state of the entire universe, the fundamental wave function that captures every possible state of the cosmos. To understand the Wheeler-DeWitt equation, let's take a step back and think about the Schrödinger equation in quantum mechanics. This equation allows us to predict the behavior of particles by describing their wave function, a mathematical function that holds all information about a particle's state, such as its position and momentum. The Schrödinger equation is critical in quantum mechanics because it tells us how the wave function of a system changes over time. The Wheeler-DeWitt equation, however, doesn't include a time variable, and this is one of its most puzzling features. In other words, it describes a timeless state for the universe. This concept, known as the problem of time, suggests that, on a fundamental level, time might not exist as we experience it. Instead, the Wheeler-DeWitt equation gives a wave function that describes every possible configuration of the universe all at once. Time, it seems, emerges only as an illusion when we look at the universe from within. To make sense of this, imagine a library containing every possible book, with each book representing a different arrangement of the universe. Each book is complete on its own, with a unique sequence of events, but none of the books have any inherent notion of time. They simply exist. If we step back and look at all the books together, we see that time is something we impose upon the sequence of events when we read through one book from start to finish. Similarly, the Wheeler-DeWitt equation suggests that the universe may exist as a vast, timeless wave function, and what we perceive as time could simply be the way we experience changes within the universe. This idea fundamentally challenges our perception. We usually think of time as a flowing river, moving forward and carrying everything with it. But in the timeless perspective of the Wheeler-DeWitt equation, all moments, the beginning of the universe, the present moment, and even distant events in the future, are simply different parts of the universal wave function. Our experience of time might be like watching a movie where all frames already exist, but we see them unfold sequentially. The Wheeler-DeWitt equation plays a central role in quantum cosmology, a field that applies quantum mechanics to the entire universe. It's a mathematical foundation for the study of the universe's wave function and the potential origins of everything. Using this framework, some physicists explore ideas about the Big Bang, suggesting that the universe might not have had a conventional beginning in time. Instead, it could have emerged from a quantum fluctuation, a spontaneous event in the quantum vacuum, which is a state of minimal energy containing potentiality for all existence. In this context, the Wheeler-DeWitt equation gives us a theoretical basis for the idea that the universe is a product of quantum phenomena. By describing every possible state of the universe, the equation implies that the universe doesn't necessarily evolve through time in the way we typically imagine. Instead, every possible state could coexist, and what we perceive as evolution is just our way of interacting with the timeless wave function. While the Wheeler-DeWitt equation is a cornerstone of quantum cosmology, it's also one of the most controversial and challenging aspects of modern theoretical physics. One major challenge is interpreting its implications without the familiar grounding of time. Many physicists and philosophers debate whether time is indeed a fundamental aspect of reality or an emergent phenomenon. Some suggest that the Wheeler-DeWitt equation hints at a block universe where all events past and future coexist as a complete entity, while others argue for the possibility of time as a dynamic feature within a deeper underlying structure. In the end, the Wheeler-DeWitt equation remains an enigma. It opens a doorway to the ultimate questions about existence, suggesting that our universe might be something profoundly different from our everyday experiences. It points to a realm where time, causality, and change are not as clear-cut as they seem, a place where the boundaries of reality blur, and we are left to wonder what the universe really is when viewed from the outside in. For now, the equation stands as a reminder of how much we still have to discover and the mysteries that lie at the edge of human understanding. The theory of everything, TOE, is one of the holy grails of modern physics. It represents an ambitious attempt to unify all fundamental forces and particles in the universe under a single theoretical framework. This quest is not merely academic. It embodies humanity's deep-seated desire to comprehend the nature of existence, the cosmos, and our place within it. To understand the significance of a theory of everything, we must explore the forces at play in the universe and the historical context that has shaped this pursuit. At the heart of this quest lies our understanding of the four fundamental forces that govern the universe. Gravitation, the force that governs the motion of planets, stars, and galaxies. It is the weakest of the four forces, yet it dominates on large scales due to its long-range effects. Electromagnetism. This force governs interactions between charged particles. It is responsible for electricity, magnetism, and light. While strong in its domain, it can be overshadowed by the gravitational pull on cosmic scales. Weak nuclear force. This force is crucial in the process of nuclear decay and plays a significant role in the nuclear reactions that power the Sun. It operates at subatomic distances and is vital for our understanding of particle interactions. Strong nuclear force. The strongest of the four forces, it binds protons and neutrons together in atomic nuclei. Its strength ensures the stability of matter as we know it. These forces govern everything from the structure of atoms to the dynamics of galaxies, yet they are described by separate theories: general relativity for gravity and quantum mechanics for the three other forces. This division leaves a gap in our understanding, one that the theory of everything seeks to bridge. The journey toward a unified theory has a rich history, marked by the contributions of brilliant minds. In the early 20th century, Albert Einstein famously struggled with his own theory of general relativity. While he was able to describe gravity elegantly, he yearned for a similar framework to explain electromagnetism. This pursuit would become central to the development of modern physics. In the mid-20th century, physicists like Richard Feynman and Steven Weinberg advanced quantum field theory, which successfully combined electromagnetism with the weak and strong forces into the standard model of part. For such instantaneous action, it must mean something is missing in our understanding. They believed that hidden variables, unknown factors yet to be discovered, would eventually explain these mysterious connections without needing spooky action at a distance. Einstein and his colleagues' skepticism was rooted in a belief that the universe is local, that objects cannot affect each other's states faster than the speed of light. However, later experiments by physicist John Bell in the 1960s demonstrated that no hidden variables could explain the phenomenon in a way that preserved locality. Bell's theorem provided a way to test entanglement's predictions, and the experimental results overwhelmingly supported quantum mechanics, not Einstein's theory of local realism. Quantum entanglement is not just a theoretical curiosity. It's the foundation for some of the most exciting technologies being developed today. In quantum computing, entanglement allows quantum bits, or qubits, to perform computations in ways that classical bits cannot. A qubit can represent both 0 and 1 simultaneously, thanks to superposition, and if multiple qubits are entangled, they can work in concert to solve complex problems at incredible speeds. This capability gives quantum computers a tremendous advantage in solving problems like cryptography, complex modeling, and simulations. Entanglement is also critical to quantum cryptography and the emerging field of quantum communication. In standard cryptography, information is encrypted and transmitted, which can be vulnerable to interception. Quantum cryptography, however, leverages entanglement to create secure communication channels. If two people share an entangled pair, they can use it to create encryption keys. Any attempt to intercept these keys would disturb the entangled particles, alerting the users to the intrusion. Quantum encryption holds promise for creating secure, unbreakable communication networks. Quantum entanglement pushes us to reconsider our understanding of reality, separateness, and connection. If entangled particles are truly instantaneously linked, then space and time as we understand them might not apply at the quantum level. In fact, some physicists suggest that entanglement could be the key to understanding space itself, proposing that the fabric of space-time might be woven from entangled particles. This possibility leads us to speculate that the connections we see at the quantum level may underpin the structure of the entire universe. This idea has profound implications not only for physics but for our philosophy of existence, as entanglement hints at a level of connectivity in the universe that transcends ordinary physical constraints. Quantum entanglement challenges our intuitions, revealing a universe that is more connected than it appears. It suggests that at the most fundamental level, particles are not isolated entities, but are part of a vast, interconnected web. Whether entanglement will one day unlock a new understanding of the cosmos or remain one of nature's most profound mysteries, it reminds us that reality is far stranger and more beautiful than we can easily grasp. And as we probe deeper into quantum mechanics, we stand on the edge of discovering how interconnected everything in the universe might truly be. Quantum field theory. Imagine a bustling city where every building, every car, and every streetlight seems separate, but is in fact part of a single, interconnected system. There's an underlying grid of electric currents, fiber optic cables, and information highways that connects it all, even though you can't see it directly. This analogy is similar to how quantum field theory, QFT, imagines the universe, not as a collection of isolated particles, but as an intricate interwoven grid of fields that stretch across space and time. In essence, QFT is a framework that unifies quantum mechanics, the study of the very small, with special relativity, the study of objects moving at high speeds. Rather than viewing particles as tiny, standalone entities, QFT describes them as excitations or disturbances in these underlying fields. Just as ripples appear in water when a stone is thrown into a pond, particles are essentially ripples in their respective fields. The theory has proven so successful that it forms the basis for our current understanding of particle physics, allowing us to predict the behavior of subatomic particles with astonishing accuracy. To understand QFT, we first need to grasp the idea of a field. In classical physics, a field is a concept that assigns a value to every point in space. For example, a magnetic field around a magnet assigns a direction and strength to every point in space around it, showing where and how strong its influence is. In QFT, fields are even more fundamental. They are the true fabric of reality. In this theory, there's a field for every particle type we know. For example, there's an electron field, a photon field for light, and fields for all the other particles. Particles aren't seen as things that move through empty space, but rather as localized vibrations within the respective fields. When we observe an electron, what we're really seeing is an excitation, a small wave, in the electron field. These fields are thought to extend across the entire universe, meaning that every point in space has the potential to host an electron, photon, or any other particle based on the behavior of its respective field. In QFT, energy plays a central role. Each particle's mass and other properties can be thought of as a form of energy stored in its corresponding field. The field itself, spread across the universe, has energy, and sometimes that energy can become concentrated to create particles. When enough energy is added to a field at a particular point, it can cause a ripple big enough to manifest as a particle with mass. Imagine waves on an ocean. Some are tiny ripples, while others swell into larger, more noticeable waves. Particles are the larger, more visible waves in this metaphor. But even in the absence of these visible waves, the ocean, the field, still exists, constantly vibrating with potential. Similarly, in QFT, even empty space is never truly empty. Fields are constantly fluctuating at tiny scales, even in what we perceive as a vacuum, giving rise to what physicists call vacuum energy, or the zero-point energy of a field. The framework of QFT underpins the standard model of particle physics, which is our best attempt to categorize and understand the fundamental particles and forces of nature. The Standard Model describes 3 of the 4 fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Gravity is notably excluded and remains one of QFT's greatest challenges. According to the Standard Model, each of these forces operates through the exchange of force-carrying particles: photons for electromagnetic force, gluons for the strong force, and W and Z bosons for the weak force. These force carriers are also treated as ripples in their own fields. When particles interact, it's essentially fields communicating with one another. For instance, when 2 electrons repel each other, this interaction can be understood as the electron fields talking through the exchange of photons, which are the mediators of the electromagnetic force. One of the strangest implications of QFT is the concept of virtual particles. According to the theory, fields are always vibrating, even in a vacuum, leading to brief appearances of particle pairs that pop in and out of existence. These virtual particles aren't directly observable, but they play a significant role in particle interactions. Virtual particles are the intermediaries that allow fields to interact. They're fleeting and don't obey the usual conservation laws, but they influence real particles' behavior. For example, the electromagnetic field's fluctuations create virtual particles that cause an electron to wiggle slightly, which gives rise to the Lamb shift, a measurable effect observed in atomic physics. Virtual particles also contribute to vacuum polarization, subtly affecting the properties of particles in ways that have been experimentally verified. While QFT has been a resounding success in explaining 3 of the 4 forces, it has struggled with incorporating gravity, which is traditionally described by Einstein's general theory of relativity. Gravity operates on a cosmic scale, shaping galaxies and black holes, while QFT primarily applies to the microscopic world of particles. Unifying these 2 frameworks into a single theory, a theory of everything, remains one of the greatest challenges in theoretical physics. One approach that physicists are exploring is quantum gravity, where gravity would also be treated as a quantum field, potentially with its own particle, the graviton. However, creating a consistent theory that combines QFT and general relativity has proven elusive, largely because gravity behaves quite differently from the other forces. Some theories, such as string theory, propose that particles aren't point-like ripples in fields, but tiny vibrating strings, which could potentially reconcile the 2 frameworks. Quantum field theory gives us a radically different picture of reality, suggesting that what we experience as particles are just localized expressions of underlying fields. This approach not only revolutionized our understanding of physics, but also paved the way for some of the most groundbreaking technologies of the modern world. Concepts rooted in QFT underlie the functionality of MRI machines, semiconductors, and even lasers. The interactions between quantum fields drive processes at the heart of chemistry and biology, influencing everything from atomic structures to chemical reactions. In a way, QFT is a reminder that the boundaries between objects, particles, and even forces are more fluid than they appear. The theory reveals that reality at the smallest scales is an intricate dance of interconnected fields, each one subtly influencing the others in a never-ending symphony. This interconnectedness lies at the heart of modern physics, opening doors to technologies and theories that might one day unravel the deepest mysteries of the universe. The Standard Model of Particle Physics. Imagine the universe as a vast theater with countless actors, each playing a role in the grand production we call reality. The Standard Model of Particle Physics is like a script that gives every particle in this universe a role, explaining how these tiny actors interact to produce everything we see, from the stars in the sky to the atoms in our bodies. It's one of the most successful theories in physics, providing a framework that classifies the fundamental particles and 3 of the 4 fundamental forces that govern the universe: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity remains a mystery outside its boundaries. At the heart of the Standard Model are the fundamental particles, which are divided into two main groups, quarks and leptons. Quarks are particles that combine to form protons and neutrons, the components of an atom's nucleus. They come in 6 types, or flavors: up, down, charm, strange, top and bottom. Up and down quarks are the most common, as they make up protons and neutrons. The others, like the exotic top and strange quarks, are found in high-energy environments such as cosmic rays or particle accelerators. Leptons include particles like the electron, which orbits the nucleus of an atom, and its less famous counterparts, the muon and tau particles. Each of these particles has a corresponding neutrino, ghostly particles with almost no mass that rarely interact with anything, passing through matter as though it isn't even there. In total, the Standard Model accounts for 12 fundamental particles, neatly organized into 3 generations that increase in mass and energy as you go up. To put this in a familiar context, imagine quarks and leptons as Lego bricks of different colors and shapes. They can be combined in various ways to build larger structures, like protons, neutrons, and atoms. These building blocks come together in predictable ways to form the incredibly diverse universe around us. In addition to the fundamental particles, the Standard Model also includes force-carrying particles which mediate interactions between particles. Each fundamental force has its own particle that acts as its messenger. Electromagnetism is mediated by photons, the particles of light, which are responsible for holding electrons in orbit around atomic nuclei. When you flip on a light switch, photons are mediating the interaction that lets you see. The strong nuclear force which binds protons and neutrons together in the nucleus is carried by particles called gluons. Gluons, unlike photons, interact only with quarks, essentially gluing them together to form protons and neutrons. The strong force is incredibly powerful, but it only operates at extremely short distances. It's what makes the nucleus stable, despite the repulsive electromagnetic force between positively charged protons. Finally, the weak nuclear force is mediated by W and Z bosons. Unlike the electromagnetic and strong forces, the weak force is responsible for processes that change one type of particle into another. For example, in radioactive decay, a neutron can transform into a proton, an electron, and an electron neutrino thanks to the weak force. It plays a vital role in nuclear reactions, including those in the Sun, where hydrogen nuclei fuse to form helium and release vast amounts of energy in the form of sunlight. One of the greatest achievements of modern physics came in 2012, when scientists at CERN's Large Hadron Collider confirmed the existence of the Higgs boson, the so-called God particle. The Higgs boson is unique in the Standard Model because it's tied to the Higgs field, an invisible field that permeates all of space. When particles interact with the Higgs field, they acquire mass. The Higgs boson itself is like a ripple in this field. To understand this, imagine the Higgs field as a pool of thick syrup filling the entire universe. When particles move through it, some encounter more resistance than others. Heavier particles like quarks experience a lot of drag and therefore gain more mass, while lighter particles like neutrinos hardly interact with it and remain nearly massless. The discovery of the Higgs boson was a monumental validation of the Standard Model, confirming how particles gain mass and why some particles are heavy while others are nearly massless. Despite its successes, the Standard Model has one glaring omission: gravity. While gravity is a fundamental force we experience in our daily lives, it doesn't fit neatly into the framework of the Standard Model. Gravity, according to Einstein's theory of general relativity, is a distortion in the fabric of space-time caused by mass. But this description doesn't mesh easily with the quantum-based Standard Model, which operates on entirely different principles. Physicists have theorized a particle called the graviton that would carry the gravitational force in a manner similar to photons and gluons for their respective forces. However, No experiment has yet confirmed the existence of gravitons, and the mathematics of gravity doesn't align well with the Standard Model's framework. This gap remains one of the most intriguing challenges in physics and has spurred ongoing efforts to unify the Standard Model with gravity under a single theory of everything, TART. The Standard Model, while remarkably successful, is still incomplete. It doesn't account for dark matter, a mysterious substance that makes up about 27% of the universe's mass, nor does it explain dark energy, a force driving the accelerated expansion of the universe. Additionally, neutrinos in the Standard Model are predicted to be massless, yet experiments have shown they have a tiny amount of mass. The Pauli exclusion principle. The Pauli exclusion principle is one of the most fundamental rules of the quantum world, dictating how particles, specifically fermions, like electrons, protons, and neutrons, behave within atoms and molecules. Named after the physicist Wolfgang Pauli, who formulated the rule in 1925, it essentially states that no two fermions can occupy the same quantum state within a given system simultaneously. This seemingly straightforward rule has profound implications, impacting everything from the structure of atoms to the stability of matter itself. To truly understand it, let's break it down with a relatable analogy and dive into why it's such a bedrock principle in physics. Imagine a multi-level apartment building where each floor represents an energy level, and each apartment on a floor represents a specific quantum state within that level. Now, say you have a large group of people, representing electrons, who want to live in this building. However, there's a strict rule. Each apartment can only hold 2 people, and these 2 people must have opposite preferences. We'll call this spin, a fundamental property of particles. When the building starts filling up, people begin occupying the apartment starting from the lowest floors, lower energy levels first. As they go up, they must abide by the building's occupancy rules. If one person is already in an apartment and has a particular preference, then the only way another person can share that apartment is if they have the opposite preference. And once an apartment has 2 people, no more can move in. They must seek higher floors. This is the Pauli exclusion principle at work. Only 2 electrons with opposite spins can occupy the same quantum state in a single orbital. If that state is fully occupied, other electrons must move up to higher energy levels or find unoccupied states. This seemingly simple restriction shapes the structure of atoms and is why electrons arrange themselves in shells and subshells around a nucleus. The key to understanding why the Pauli exclusion principle matters is understanding quantum states, and spin every electron in an atom is defined by a unique set of quantum numbers, which together describe its energy, angular momentum, and spin direction. These quantum numbers effectively represent an address for each electron's location in the atom. An electron's spin is an intrinsic property like charge or mass, but unlike these, it doesn't have a direct classical analogy. Spin doesn't imply literal spinning. Instead, it represents a quantum state characteristic that, in the case of electrons, can take one of 2 possible values, up or down. The Pauli exclusion principle dictates that within any single orbital, like an apartment in our analogy, no 2 electrons can have the same spin direction. One must be up, and the other must be down if they share the same space. The Pauli exclusion principle is critical in explaining why atoms have their own particular structure. Take, for instance, the simplest atom, hydrogen, with just 1 electron. Since this electron has no competition, it fills the lowest energy state. Moving up to helium with 2 electrons, they can both fit in the same lowest energy level, provided they have opposite spins. This forms a complete apartment, the 1s orbital, for helium. However, when we reach lithium, which has 3 electrons, a challenge arises. With the 2 lowest spots filled, the 3rd electron must occupy the next available energy level, starting a new floor in our building. This organization continues, giving rise to the familiar electron configurations for each element and forming the basis of the periodic table. Each additional electron fills the lowest available orbital while obeying Pauli's rule, resulting in the intricate and structured arrangement of shells and subshells. One of the most remarkable consequences of the Pauli exclusion principle is its role in making matter stable. Without this principle, electrons could all occupy the lowest energy state around an atom's nucleus, collapsing into a tiny, dense ball. Instead, the exclusion principle enforces that each electron occupies a distinct state, keeping them spread out over different energy levels. This distribution means that atoms take up space and resist compression, creating the solid matter we interact with daily. Consider white dwarf stars, remnants of stars that have exhausted their nuclear fuel and collapsed under gravity. In these stars, matter is densely packed, but the Pauli exclusion principle prevents the electrons from occupying the same quantum states, providing a counterpressure against gravity. This balance creates what's known as electron degeneracy pressure, which supports the star's structure and prevents it from collapsing further. This same principle also governs neutron stars, where the Pauli exclusion principle applies to neutrons instead of electrons. In chemistry, the Pauli exclusion principle explains why atoms bond in specific ways. Take the water molecule H2O. The two hydrogen atoms bond with the oxygen atom because they can share electrons in a way that fills the quantum states available in the oxygen atom's outer shell. Pauli's principle ensures that these shared electrons must have opposite spins, allowing them to coexist in the bonding orbitals. This rule not only dictates the shape of molecules, but also affects their chemical properties and reactivity. For larger atoms, like those with many electrons, the principle also influences electron configurations, dictating how electrons fill shells and subshells in a predictable order, the Aufbau principle. This orderly filling is what gives rise to the specific chemical behavior of elements, defining reactivity, bonding preferences, and other chemical properties that underpin the diversity of matter. Interestingly, the Pauli exclusion principle also plays a role in the emerging field of quantum computing. Quantum bits, or qubits, in a quantum computer can represent both 0 and 1 simultaneously due to quantum superposition, but they must still adhere to certain quantum rules. While Pauli's principle itself applies primarily to fermions, understanding the exclusive behaviors of quantum states helps researchers engineer systems that exploit quantum behaviors without interference, opening doors to more efficient computation. In essence, the Pauli exclusion principle defines the architecture of the quantum world. It provides the structural basis for atoms, determines the organization of the periodic table, stabilizes matter, and even impacts stellar evolution. Pauli's insight revealed that nature's smallest particles obey a strict occupancy rule, a rule that shapes our macroscopic world in ways that are both fundamental and elegant. The exclusion principle reminds us that even in the quantum world, where particles defy ordinary logic and behave in bizarre, probabilistic ways, there exists a deep and organizing structure. It is a principle that quietly governs the universe, ensuring that each particle finds its place while preserving the intricate order of atomic and molecular structures, ultimately allowing for the existence of the vast and stable universe we inhabit. Black holes and Hawking radiation. Black holes and Hawking radiation are two of the most intriguing and mind-bending phenomena in astrophysics, and they reveal the complex dance between gravity, quantum mechanics, and thermodynamics in the universe. Black holes, often seen as cosmic voids of no return, are not just the ultimate traps in space, but also sources of strange quantum processes. Through Stephen Hawking's groundbreaking work, we learned that black holes are not entirely black but can emit a faint, mysterious radiation, Hawking radiation, slowly losing mass until they might ultimately vanish. Let's dive deeper into what black holes are, how they form, and what this elusive Hawking radiation really means. Black holes are born from the deaths of massive stars. Imagine a star far bigger than our Sun, burning through its fuel over millions or even billions of years. The star's core fuels fusion reactions that produce immense outward pressure, counteracting the powerful gravitational pull trying to collapse it. But once the fuel runs out, gravity wins this cosmic tug-of-war, and the star's core collapses inward under its own weight. This inward collapse crushes the core to an unimaginable density, creating a gravitational field so strong that not even light, the fastest thing in the universe, can escape. The boundary beyond which escape becomes impossible is called the event horizon. For anything, including light, crossing this boundary means plunging inevitably toward the black hole's core, or singularity, a point where density becomes infinite, and the known laws of physics break down. To picture the event horizon, think of a canoe on a river heading towards a waterfall. Far upstream, paddling away from the edge is easy, but as you get closer to the waterfall's edge, the current pulls you faster and faster until you reach a point where, no matter how hard you paddle, you cannot avoid going over the edge. This point of no return is like the event horizon. Anything that crosses it, from particles to entire stars, is inexorably pulled towards the black hole's singularity. In 1974, Stephen Hawking made a stunning prediction that challenged the traditional view of black holes. He proposed that black holes are not completely black but emit a faint radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, arises from the strange behavior of virtual particles in quantum mechanics. In quantum mechanics, even the vacuum of space is not truly empty. It constantly produces pairs of particles and antiparticles, one positive, one negative, that quickly annihilate each other. Near the event horizon, however, something unusual can happen. If a particle-antiparticle pair forms just at the boundary, one particle can be captured by the black hole while the other escapes into space. The one that escapes becomes real, contributing to the energy radiated by the black hole, while the one that falls in has negative energy, effectively reducing the black hole's mass. To visualize Hawking radiation, imagine a busy dance floor where dancers form pairs and briefly spin together before parting. However, if one dancer is pulled off the floor, symbolizing the particle caught by the black hole, while the other remains free to continue dancing, the escaping particle, the dance floor, loses a bit of energy. Over time, as more and more dancers leave, the floor becomes less crowded, and eventually, the entire room empties. Similarly, as a black hole emits Hawking radiation, it slowly loses energy and mass. Hawking radiation means that black holes can, in theory, evaporate over time. However, this is an incredibly slow process. For a black hole the mass of our Sun, it would take far longer than the age of the universe to evaporate. Only tiny black holes potentially created during the early universe or in high-energy conditions might evaporate within a reasonable time frame, producing bursts of radiation as they vanish. This evaporation process introduces a fascinating paradox. If a black hole fully evaporates, what happens to all the information it absorbed? In physics, the information paradox raises questions about whether information about the particles that fell into the black hole is destroyed or somehow preserved. Since quantum mechanics suggests information cannot be lost, this paradox has led to intense research and debate, driving physicists to search for a deeper understanding of both black holes and quantum gravity. One of Hawking's contributions was showing that black holes obey a form of thermodynamics. Just as a regular object's temperature and energy can be measured, a black hole has temperature, entropy, and can radiate energy through Hawking radiation. The entropy of a black hole, it turns out, is proportional to the surface area of its event horizon, rather than its volume. This finding ties black hole physics to the second law of thermodynamics, which states that entropy disorder tends to increase over time in an isolated system. This thermodynamic perspective suggests that black holes are not just regions of extreme gravity, but also hold insights into the nature of space, time, and information itself. Hawking's work paved the way for theories that attempt to unify general relativity and quantum mechanics. potentially bringing us closer to understanding the fundamental structure of the universe. Hawking's contributions transformed our view of black holes from cosmic vacuums into dynamic thermodynamic objects with far-reaching implications. Black holes are no longer just cosmic anomalies but hold clues to deep cosmic laws and the nature of reality itself. The existence of Hawking radiation suggests that the universe operates in ways we're only beginning to understand, and his insights continue to drive theoretical and experimental research in physics. Black holes and Hawking radiation show us that the universe is full of mysteries waiting to be unraveled. From the vastness of space-time to the tiniest quantum fluctuations, these phenomena remind us of the delicate balance between the cosmic forces that shape everything. Hawking radiation provides a bridge between the immense gravitational pull of black holes and the subtle quantum fluctuations that govern the smallest particles, linking the vast and the minuscule in one of the most profound ways in physics. As we continue to study black holes, we may uncover deeper truths about the very fabric of the cosmos, perhaps answering age-old questions about the nature of space, time, and existence itself. String Theory Basics. String Theory Basics offers one of the most ambitious attempts to unite all fundamental forces of nature under one theoretical roof. By suggesting that particles aren't actually point-like, but are made up of tiny vibrating strings, string theory provides a radical new framework for understanding the universe's deepest structure. From uniting gravity with quantum mechanics to hinting at hidden dimensions, it promises a grand tapestry for connecting the very large and the very small. But before diving into these implications, let's start with the basics: what string theory is, why it was proposed, and what it tries to accomplish. At the heart of modern physics are two extremely successful theories: general relativity and quantum mechanics. General relativity, proposed by Einstein, is a theory of gravity that describes the universe at large scales, like stars, galaxies, and the cosmos itself. Quantum mechanics, on the other hand, governs the tiny world of particles, like electrons and photons. Each theory is remarkably accurate within its domain, but behaves in completely different ways. And when scientists try to combine them to understand extreme environments, such as the core of a black hole or the moment of the Big Bang, they encounter paradoxes and infinite values that simply don't make sense. This gap between gravity and quantum mechanics has been one of the biggest puzzles in theoretical physics. String theory is one of the most promising approaches to bridging this gap by proposing that at the tiniest scale, matter isn't made up of particles but tiny, one-dimensional strings. Just as different notes on a violin string produce different sounds, different vibrations of these fundamental strings give rise to different particles and forces. In everyday life, we think of particles as tiny points with no dimensions, like infinitesimally small dots that make up all matter. But in string theory, these particles are actually tiny vibrating strings, roughly 100 billion times smaller than an atom. Each string can vibrate at different frequencies, and each pattern of vibration corresponds to a specific particle. So an electron, a photon, or a quark are just different notes, or vibrational patterns of these fundamental strings. Imagine a guitar string which can be plucked to produce different musical notes. In a similar way, strings in string theory vibrate to produce different particles. This analogy helps explain why we see such a diverse orchestra of particles in nature. They are all manifestations of the same fundamental strings, just vibrating in different ways. One of the reasons string theory is so appealing is that it naturally incorporates gravity. In fact, when physicists worked out the math of string theory, they discovered that one of the vibrations corresponds to a particle called the graviton, which is responsible for the force of gravity. This was revolutionary because traditional quantum mechanics didn't have a place for gravity. Strings also smooth out some of the infinities and paradoxes that arise when trying to reconcile quantum mechanics and gravity. In simpler terms, by stretching out into strings rather than being point-like, these tiny bits of matter don't cause as many spikes in the mathematics. This makes string theory a compelling candidate for a theory of everything, meaning it could potentially explain all the fundamental forces and particles in the universe under one unified framework. Here's where string theory gets even stranger. For the math of string theory to work, it requires more than the familiar 3 dimensions of space and 1 dimension of time. In fact, it suggests there may be up to 10 or 11 dimensions in total. The extra dimensions are theorized to be curled up so tightly that we don't see them in our everyday lives. To imagine this, think of an ant walking along a garden hose. To us, the hose looks like a simple line, but the ant sees it as 2-dimensional because it can move around the surface of the hose. The idea of extra dimensions in string theory is similar. They're so tiny and tightly packed that we only perceive the large-scale dimensions. These hidden dimensions are thought to shape the properties of particles and forces, giving each string a unique vibrational pattern that we observe as different types of particles. There isn't just one version of string theory. Initially, there were 5, each with different mathematical details. However, in the 1990s, physicists discovered that these 5 versions are connected by a larger framework called M-theory. Or M-theory suggests that all string theories are just different perspectives of a single, more profound theory. It also introduces the idea of branes, short for membranes, multidimensional objects that may represent other types of matter or energy. This M-theory view of strings adds even more depth to the model, suggesting that strings may not just be one-dimensional, but could have different dimensions, much like sheets or blobs that could be floating in a larger multidimensional universe. And in this universe, our entire observable world could be a brane, like a bubble floating in a vast cosmic sea. String theory is mathematically beautiful and has opened up exciting possibilities, but it also faces significant challenges. One issue is that it's very hard to test string theory through experiments, as the strings themselves are incredibly small and require energy levels far beyond what we can currently produce. Additionally, string theory has a huge landscape of possible solutions, potentially as many as 10 circumflex 500 different universes, each with its own physical laws. This makes it difficult to identify a unique solution that corresponds to our own universe. Some critics argue that without experimental evidence, string theory risks becoming more of a philosophical or mathematical exercise than a physical theory. However, proponents believe that string theory may eventually provide testable predictions, and its mathematical consistency offers a framework for understanding the universe at a level that no other theory currently achieves. In a poetic sense, string theory suggests that all of existence could be thought of as a cosmic symphony, with each particle a different note in a universal melody. These tiny vibrating strings are like the most fundamental music of nature, producing everything from the lightest photon to the heaviest particle, simply by changing their vibrational pattern. And although we still have much to understand, string theory continues to be one of the most promising approaches to uniting the seemingly incompatible worlds of quantum mechanics and gravity. As we study the language of these strings, we may be uncovering the very notes of creation itself, a melody woven through dimensions and space-time, and one that could ultimately help us understand the deepest mysteries of existence. Extra dimensions and brane theory. Extra dimensions and brane theory introduces a revolutionary way to understand the fabric of reality. Where we're used to a 3-dimensional world with length, width, and height, and a 4th dimension of time, brane theory suggests there is much more hidden just beyond our perception. In string theory, the idea of extra dimensions is essential, shaping particles, forces, and potentially even other universes. In this section, we'll explore what extra dimensions and branes could mean for our understanding of the universe, the possible hidden realms they imply, and how they bridge the boundaries of physics. Imagine you're standing in a field. You see people, buildings, trees, and skies, all in 3 spatial dimensions, length, width, and height. You can walk forward, backward, side to side, or jump up. Now, picture adding another direction beyond the ones we experience, a tiny dimension curled up so tightly that it's invisible to us. This isn't easy to grasp, but consider an ant on a thin wire. As it moves along the wire, it's free to travel up, down, or sideways. If the wire were thin enough, you might see only a straight line, but for the ant, it's a complex, multidirectional world. In brain theory, physicists propose that our own universe might be like that tiny wire in the example, embedded within an enormous multidimensional space called the bulk. We see only our familiar three dimensions, but hidden within the bulk may be additional spatial dimensions, invisible yet fundamental to how the universe works. String theory suggests there may be as many as 10 or 11 dimensions, with our observable world occupying only a fraction. To understand brains in brain theory, think of them as multidimensional surfaces or sheets floating in this multidimensional bulk. The term brain comes from membrane, and it can take on various forms. A one-dimensional brain is a simple string, a two-dimensional brain is like a sheet, and so on. Our universe could be a three-dimensional brain called a three-brain, within this larger multidimensional space. In this way, brains are surfaces on which all the particles and forces we observe, like light, electromagnetism, and nuclear forces, are stuck. If we're living on a brain, everything we perceive is bound to it. Think of it like a soap bubble floating in air. If you're an ant living on the surface of the bubble, you can move freely across it, but you can't leave the surface. The air around you, representing higher dimensions, exists, but you can't reach it because you're bound to the bubble's surface. In a similar way, we might be bound to our three-brain and unable to perceive or interact with the other dimensions of the bulk directly. Danielen, the concept of extra dimensions is critical in string theory because it provides the mathematical framework needed to make the theory consistent. In other words, string theory works only if we accept the presence of these additional dimensions. Extra dimensions allow for various vibrational patterns in strings, leading to different particles and forces. Furthermore, they could offer insight into fundamental questions like why gravity is so much weaker than other forces. Here's where it gets even more interesting. Gravity, unlike other forces, might not be confined to our three-brain. Physicists theorize that gravitons, the particles associated with gravity, could leak into the bulk, explaining why gravity is so weak in our observable universe compared to other forces like electromagnetism. Just as some sound escapes from a closed room, gravity might escape into higher dimensions, spreading out across the bulk and reducing its strength in our brain. Brain theory opens up the possibility of parallel universes or other brains coexisting within the same bulk. Each brain could contain its own distinct universe with its own laws of physics. Imagine again our soap bubble floating in the air. Now imagine other bubbles floating nearby. Each bubble, or brain, represents a different universe with its own unique physical properties. These brain universes could be separated by incredibly small distances in the bulk, invisible and inaccessible to us, but still very real, innate. In some theories, interactions between brains could even lead to cosmic events. For example, some physicists speculate that the Big Bang, the event that started our universe, could have been the result of two brains colliding in the bulk. This collision could have created the enormous energy required for the birth of our universe. In this view, the Big Bang wasn't the start of everything, but simply the start of our particular brain universe. One of the most challenging aspects of brain theory and extra dimensions is the lack of direct evidence. Since we can't directly perceive or measure these dimensions, proving their existence is a formidable task. However, physicists are searching for hints in experiments, particularly in particle accelerators like the Large Hadron Collider, LHC. The LHC could, in theory, detect signs of extra dimensions if particles created in high-energy collisions seem to disappear or if they produce gravitational waves that behave in ways not explainable by standard models. Additionally, scientists are studying gravitational waves, ripples in space-time that spread across the universe potentially interacting with higher dimensions. If they detect anomalies in these waves, it could suggest that some gravitational energy is leaking into extra dimensions, lending credence to brain theory. Brain theory and the concept of extra dimensions remain speculative, but are essential components of modern physics, helping scientists refine ideas about space, time, and the universe's structure. While these ideas are yet to be proven, they provide a stunning glimpse into what might lie beyond our observable world, showing that reality could be far more complex and fascinating than we ever imagined. In brain theory, we're part of a broader multiverse where our universe is just one layer among many. The other dimensions might be hidden but not irrelevant, quietly shaping the structure of everything we experience. Through theories like brain theory, science continues its quest to peel back the layers of reality and show us a universe richer, more mysterious, and filled with hidden possibilities beyond our everyday understanding. Quantum loop, gravity, quantum loop gravity, QLG, or loop quantum gravity, LQG, is a theory that attempts to merge the two most successful frameworks of modern physics, quantum mechanics and, where it is, general relativity. While quantum mechanics governs the behavior of subatomic particles with uncanny precision, general relativity explains the force of gravity and the large-scale structure of the cosmos. The issue is that these two theories, despite their immense success, don't naturally fit together. The challenge of combining them into a cohesive framework is one of the greatest quests in modern theoretical physics. The loop. Quantum gravity offers an alternative to string theory, another popular candidate for quantum gravity, and provides a unique approach to understanding how space-time itself might be quantized or broken down into discrete chunks at the smallest scales. To understand the motivation behind quantum loop gravity, let's first look at the mismatch between general relativity and quantum mechanics. General relativity describes gravity not as a force, but as the curvature of space-time itself, warped by the presence of mass and energy. Think of space-time as a flexible sheet, and objects like planets and stars as weights placed on it, creating dips and bends. This framework works exceptionally well for explaining large-scale structures like galaxies and black holes. On the other hand, quantum mechanics deals with particles and forces on extremely small scales where uncertainty and probability rule. In quantum mechanics, forces such as electromagnetism are transmitted by particles, like photons for light. If we try to apply these quantum principles to gravity, we run into serious issues. The smooth fabric of space-time described by general relativity clashes with the jittery, probabilistic world of quantum particles. The very idea of a smooth, continuous space-time breaks down at incredibly tiny distances, such as those near the Planck scale, a length of about 10 circumflex 35 meters, far smaller than any distance we can measure. Quantum loop. Gravity provides a novel solution to this problem. Instead of thinking of space-time as a continuous, unbroken fabric, LQG proposes that space-time itself is made up of tiny, discrete loops, much like how matter is composed of atoms. These loops are incredibly small, on the order of the Planck length, and they interweave to form a spin network, which is essentially the scaffolding of space. In this picture, space isn't a smooth sheet, but a network of interconnected loops, similar to a mesh or a grid. These loops represent the quantum states of space-time. Importantly, this means that space is quantized, just as matter and energy are quantized in quantum mechanics. There is no such thing as infinitely small space. Instead, space comes in finite, indivisible units. Third, time is also quantized in LQG, meaning that at extremely small scales, time doesn't flow smoothly but progresses in discrete jumps. This is a radical shift from our usual understanding of space and time, which seem to flow continuously in everyday experience. But at the quantum level, continuity breaks down. In LQG, the structure of space is described by what are called spin networks, which are mathematical graphs that represent the quantum state of space-time. Each edge of the graph corresponds to a quantum of space, and the nodes where edges meet represent regions of space with specific properties, such as volume. As the universe evolves, these spin networks change, with their structures shifting and reshaping over time. To visualize this, imagine a web of interconnected loops, the spin network, that continuously morphs and reshapes itself. But there is an additional layer of complexity. These changes don't happen smoothly, but in discrete, quantized steps. When we consider not just space, but also the flow of time, this evolving spin network becomes what's called spin foam. Spin foam is the 4D version of the spin network, representing both space and time in a quantum universe. It's like a constantly shifting foaming structure where space and time emerge dynamically from these quantum interactions. One of the most exciting aspects of quantum loop gravity is how it eliminates singularities, the infinite densities and curvatures that arise in general relativity, such as those found at the center of black holes or at the Big Bang. In classical general relativity, when you try to trace the history of the universe back to its very beginning, you encounter a singularity, a point of infinite density where the laws of physics break down. However, in LQG, space-time is quantized, so it never reaches the infinite densities predicted by general relativity. The loops of space-time act as a natural buffer against such extremes, preventing the formation of singularities. For instance, instead of a singular Big Bang, LQG predicts a big bounce, where the universe collapses to a minimum size and then expands again. This idea aligns with some modern cosmological theories that suggest the universe could undergo cycles of contraction and expansion. In LQG, geometry itself becomes a dynamic, evolving entity at the quantum level. This is one of the most profound consequences of the theory. Geometry is no longer a static backdrop in which events unfold, but is instead a fluctuating, interactive part of reality. The shape of space can change, twist, and evolve, and these changes affect the physical properties of the universe. At the smallest scales, geometry is defined by quantum states, and the familiar notions of distance and volume become probabilistic. The discrete nature of space-time also means that some familiar concepts, such as continuous motion or smooth geometry, no longer hold. Instead, objects jump from one location to another in a quantized fashion, just like how electrons jump between energy levels in atoms without passing through intermediate states. Quantum loop. Gravity offers a compelling vision of a universe where space and time themselves are woven from quantum threads. By breaking away from the idea of a smooth, continuous space-time, LQG attempts to solve some of the deepest problems in physics, including the clash between general relativity and quantum mechanics. While still in development, LQG is a bold step toward understanding the quantum nature of gravity and the fundamental structure of reality itself. This approach opens up exciting new possibilities for understanding black holes, the origins of the universe, and the ultimate fate of the cosmos. If correct, quantum loop gravity could reveal a universe that is far stranger and more interconnected than we ever imagined. The holographic principle. Imagine walking into a room with a vast collection of books, each filled with detailed information. Yet, what if you discovered that all the information in these books could be encoded on a flat surface, like the walls of the room? This analogy offers a glimpse into one of the most mind-bending ideas in theoretical physics, the holographic principle. At its core, this principle suggests theoretical physics. This model describes how particles interact via these forces, but it doesn't incorporate gravity, leaving a significant piece of the puzzle unsolved. The inability to reconcile gravity with quantum mechanics is often likened to trying to fit two puzzle pieces that were designed for entirely different puzzles. While quantum mechanics explains the behavior of the very small, atoms and subatomic particles, general relativity explains the very large, planets, stars, and galaxies. The quest for a theory of everything is about finding the framework in which both can coexist harmoniously. One of the leading candidates for a theory of everything is string theory. This theory posits that the fundamental building blocks of the universe are not point particles, but rather tiny vibrating strings. These strings can oscillate in different modes, and the specific vibrations correspond to different particles. For instance, one mode of vibration might represent an electron, while another could represent a quark. String theory also introduces the idea of extra dimensions, dimensions beyond the familiar 3 of space and 1 of time. While we experience a 4-dimensional universe, string theory suggests that additional dimensions may exist curled up in such a way that they remain undetectable at human scales. Imagine a garden hose viewed from a distance. It appears one-dimensional, but upon closer inspection, it reveals a circular cross-section representing additional dimensions. But one of the key strengths of string theory is its potential to unify all 4 fundamental forces. By incorporating gravity into a quantum framework, it offers hope for a consistent and comprehensive understanding of the universe. However, string theory remains largely theoretical, with much work required to make testable predictions. An alternative approach to achieving a theory of everything is loop quantum gravity, LQG. This theory also seeks to unify gravity with quantum mechanics, but does so differently from string theory. LQG proposes that space-time itself is quantized, much like energy levels in an atom. Instead of treating space-time as a smooth continuum, LQG suggests that it consists of discrete, tiny loops that form a network. Imagine a fabric woven from countless tiny threads, each thread representing a fundamental unit of space. As these loops interconnect, they create the very fabric of our universe. LQG offers a promising path to understanding the quantum properties of gravity, but like string theory, it has yet to yield definitive experimental evidence. The quest for a theory of everything is not merely about the mathematics or physics. It also raises profound philosophical questions. If we find a unified theory, what does that mean for our understanding of the universe? Are we mere observers in a predetermined cosmos, or do we have agency within it? Moreover, how would such a theory reshape our understanding of concepts like causality, free will, and the nature of reality itself? Some physicists and philosophers argue that a theory of everything might reveal an underlying simplicity to the universe, a final answer to the question of existence. Others caution that the universe is inherently complex, and a single theory may never capture its full richness. As we continue our exploration of the universe, the search for a theory of everything remains one of the most exciting and daunting challenges in physics. While theories like string theory and loop quantum gravity offer tantalizing possibilities, we are still far from a conclusive solution. The journey toward understanding the universe, however, is as significant as the destination itself. Each step taken in this pursuit not only deepens our knowledge of the cosmos, but also unveils the beauty and complexity of existence. The theory of everything, if realized, could provide a framework that transforms our understanding of reality, unifying the cosmic tapestry in which we all reside. In the end, the pursuit of a theory of everything is a testament to humanity's unyielding curiosity, a desire to understand not just how the universe works, but why it exists at all. And while we may not have all the answers today, the journey continues to inspire and ignite the imagination, reminding us that we are all part of an extraordinary cosmic story waiting to unfold. The Omega Point Theory. The Omega Point Theory is a captivating concept that merges philosophy, theology, and theoretical physics into a profound vision of the universe's ultimate destiny. Proposed by the French Jesuit priest and philosopher Pierre Teilhard de Chardin, this theory posits that the universe is evolving toward a final state of complexity and consciousness, culminating in a singularity of divine love and knowledge known as the Omega Point. To unpack this idea, we must explore its philosophical roots, its implications for the future of humanity, and its connections to contemporary scientific thought. Teilhard de Chardin was not only a priest but also a paleontologist and geologist, a background that informed his thinking about the evolution of life and consciousness. In his view, evolution was not just a biological process, but a spiritual one. He believed that the universe was moving towards a higher state of complexity and consciousness, which he termed the omega point. This point symbolizes the culmination of evolution, where all individual consciousnesses converge into a unified, collective consciousness. To illustrate this concept, consider the growth of a tree. In its early stages, a tree is a simple seed, but as it develops, it branches out, creating a complex network of leaves, flowers, and fruits. Eventually, this tree not only supports itself, but contributes to its environment, fostering life around it. In a similar way, the omega point represents the ultimate expression of complexity in the universe, where all forms of consciousness unite to create a richer, more profound existence. Teilhard's vision encompasses not just human evolution, but the evolution of the entire cosmos. He proposed that as the universe ages, it moves from a state of chaos and simplicity toward greater complexity and order. This evolutionary process is driven by a teleological impulse, an inherent tendency toward self-organization and increasing complexity. The journey to the omega point can be likened to a river flowing toward the ocean. Along its path, the river gathers tributaries, merges with other streams, and transforms the landscape. As the river flows, it shapes the environment, carving valleys and nurturing life. Similarly, humanity and the universe are on a trajectory toward unity, gathering experiences and knowledge along the way, ultimately contributing to a larger purpose. Central to the omega point theory is the role of consciousness. Teilhard believed that consciousness is not merely a byproduct of biological evolution, but a fundamental aspect of the universe itself. Just as particles combine to form atoms and atoms combine to form molecules, consciousness evolves from simple awareness to a more complex collective consciousness. Imagine the Internet as a metaphor for this evolution. Initially, it was a network of isolated computers, each serving its own purpose. As more devices connected, the network grew in complexity and utility, allowing for a communication, collaboration, and the sharing of ideas. In a similar fashion, individual human consciousnesses contribute to a collective awareness that grows and evolves over time, moving toward the omega point, or tertiary. While Teilhard's ideas are deeply philosophical and spiritual, they resonate with some contemporary scientific theories. For example, the concept of the Big Crunch suggests that the universe may eventually stop expanding and collapse back into a singularity. This point of convergence bears a striking resemblance to the omega point. The notion that all matter and energy could eventually return to a singular state aligns with Teilhard's vision of convergence. Moreover, the field of cosmology explores concepts such as complexity theory and emergent behavior, which examine how complex systems evolve from simple interactions. These scientific frameworks echo Teilhard's belief in the universe's trajectory toward increased complexity and unity. The omega point also has significant theological implications. For Teilhard, this ultimate convergence represents a union with the divine, an encounter with God that transcends individual existence. He posited that as humanity evolves, it draws closer to this divine reality. This perspective challenges traditional views of God as a distant creator, presenting a more dynamic relationship between the divine and the evolving universe. In this sense, the omega point becomes a symbol of hope, suggesting that despite the chaos and suffering in the world, there is a meaningful direction to existence. It invites individuals to engage with their spiritual journeys, fostering personal and collective growth toward this ultimate reality. As we contemplate the implications of the omega point theory, we are led to consider our role in this grand narrative. Teilhard believed that humanity's collective actions and choices are instrumental in shaping the future. Our pursuit of knowledge, compassion, and connection contributes to the evolution of consciousness. In a world marked by division and conflict, the Omega Point serves as a reminder of our interconnectedness. Just as the tree supports its environment, our individual actions can foster unity and understanding, nurturing the collective consciousness. The more we embrace collaboration and empathy, the closer we move toward the Omega Point. The Omega Point theory is a profound and hopeful vision of the universe's ultimate destiny. It challenges us to think about the nature of evolution, consciousness, and our relationship with the divine. As we navigate our complex world, we are reminded that we are part of a greater tapestry, woven together by shared experiences, aspirations, and dreams. In our pursuit of knowledge and understanding, we are not merely observers of the universe, we are active participants in its unfolding story. The Omega Point invites us to embrace our roles as co-creators of a collective future, guiding us toward unity, complexity, and a deeper understanding of existence. As we reflect on our place in this cosmic narrative, we can find hope and purpose in the journey toward the Omega Point, where all consciousness converges into a harmonious whole.